asked each of the teams to stick to their 30-minute slot. So that's 20 minutes for the presentation, 10 minutes for questions, and the screen sharing facility will be enabled. And what I'm aiming to do is at the end of each presentation, before we go into the questions, I'm just going to ask the DSTL person or perhaps the PA person who was in that team for their feedback as the end user, which is what we did in January. And that's really important as well to get the context. So I think that's all I had to say. And so we're going to do it nice and simply. We're going to run through in number order. So the first one is understanding the fundamental performance limit of a distributed RF sensor system. And I think that was one which Tony Mulholland was leading. I don't know who's going to be giving the presentation, but please do fire away.
Okay, thank you very much. And thank you to all the organisers doing an outstanding job. And it's been a great week. And yeah, it's been great fun working on this challenge. I was severely out of my comfort zone, so I'm really relying on the other guys, but it's been great fun. So my job is to really remind you of the challenge. I'll introduce the teams. And let me see if I can just get the controls to work here. Yeah, so I'll introduce the team that's before you. And so we had Joe Kernicki from DSTL and James Matthews from PA Consulting, who were the adult supervision in the room. The rest of us you can see there. So I'll kick off. I'll hand over to David Allwright, who will then hand over to Alistair and bring it back to myself. So let's remind ourselves about the challenge description. So there are radio frequency sensors. So they're listening to, they're passively listening to electromagnetic waves. And that could be for a range of reasons. You'll see later on, just to get a bit concrete, we focused on geolocation, but it doesn't necessarily have to be that. And of course, there's some errors associated with what has been sent and recorded at various stages in the pipeline from the raw wave to what we receive. And therefore, there is some limit as to how well such a system can perform. And the challenge was to try and derive a mathematical approach to look at this fundamental limit. And if we knew the fundamental limit, then of course we can benchmark where we are at the moment against that, and that would help with investment decisions. You know, if it's sort of diminishing returns, then we might say, well, there's not much point investing huge amount for little reward. Or if there's a big gap to this limit, then that would encourage activity. So this was the picture we saw at the start of the week. So there is a sensor that is emitting, that's transmitting here, that we're trying to detect, and we could have all sorts of sensors measuring that and trying to, say, locate that sensor. And it's a very complicated picture of pipeline of things that can go wrong or can propagate uncertainty through that. So there'll be errors in the measurement, and that ultimately will cause some error in the purpose of the system. As I say, we'll look at geolocation as a particular case. So the question was, how can we start to describe a system in a sort of abstract way that would yield to some limits, to some fundamental limits being achieved? How would having a number of sensors feed into that? How could we aggregate that up with a number of sensors? And there was a feeling that perhaps techniques from information theory and such areas might be a good place to go for that. So that was really our beginnings. But I think now I'll hand over to David, who'll take us through some of what we looked at this week.
Okay, thank you, Tony. So James Matthews pointed us to a paper by Geoffrey Andrews that was looking at stochastic geometry in addressing questions about mobile phone network coverage. So in that paper, the base stations of the mobile phone network were modeled as a random point process in the plane, and so the signal to interference to noise ratio sort of took the usual form, except that the XIs, the position of the base stations, were random. And so James asked whether we could do some kind of comparable study for, say, geolocation with a random array of sensors. Could we study how its accuracy varied with the accuracy of the sensors, with the density of the Poisson process? So if we go on to slide 7, the next few slides are going to describe our attempt to do that. So first of all, we're going to describe roughly how time difference of arrival at geolocation works. And then we're going to apply how that happens when you have a random set of sensors. So in TDOA geolocation, you assume there's an unknown point here denoted by Y, which emits some kind of bang at time t0, and you will receive that at some sensor xi at a time which is t0 plus the travel time y minus x divided by c plus some random error. And so if the sensors were all equally weighted, then you would try to minimize this sum of squares s that's written down here, and that would be a way of estimating your position y hat, estimated position of the contact, and the t0 is a nuisance parameter there. And if the sensors were all Gaussian with the same variance, you would interpret this quantity as a maximum likelihood estimate. Next slide, please. So yes, if the sensors have got different standard deviations, then rather than an equally weighted sum of squares, you would have this modified S here, which has got W's that are proportional to 1 over sigma I squared. So the sensors with large standard deviation get lower weighting in the sum of squares. Another issue would be that the sensors themselves may not exactly be at the positions we think they are, xi, and so there would be errors introduced by that. Now, one issue is that estimating the time difference of arrival, these are not done by just calculating the arrival times and working out the difference of them. Rather, you take the two signals received at the two sensors, and roughly speaking, you cross-correlate them and try to find the lag at which the peak of the cross-correlation occurs. And that will give you some delta t ij, the time difference between the signals at I and j. If that time difference is known exactly, then it defines that the distance of y from x minus the distance of y from xj is some given constant. So that defines one branch of a hyperbola in the plane on which the point lies. These delta tij's determined from the different sensors will not necessarily be consistent. Ideally, they should obey that delta tij plus delta tjk plus delta tki equals 0, but the noisy estimates may not obey that. So next slide, please. One way to try to correct for that is that the matrix of these time differences must in fact be of rank 2. So you could use finding the closest rank 2 approximation to the time difference matrix as a way of sort of forcing the time differences to a consistent set. I think there are other ways of doing that as well. Next slide, please. So then Tony helpfully suggested that when we try to do this with a random array of sensors, it might be better to start in just one dimension. So this slide is much as before, except in the second bullet. Let's draw attention to this. We're going to assume that as a sensor gets further away from the contact point, the variance increases. So this quantity sigma squared, function of x minus xj, will be some increasing function of distance. One of the effects that contributes to that is that sensors further off are receiving a lower signal to noise ratio. So naturally, they're subject to greater errors in timing some feature in the signal they receive. Alistair will describe proper models for this later, but at the moment, this is just sigma squared as a function of distance. So we're going to take the simplest case where we have Gaussian noise, and we hope by the Rao-Blackwell theorem that the variance in estimated position will in such a case be asymptotic to the Cramer-Rao lower bound. And so next slide, please. We go on to compute that in the usual way. So first of all, we compute the Fisher information matrix conditional on certain positions of the sensor, so these xj's. Then we're going to want to take the expectation of that information matrix, now thinking of the xj's as being random variables given by a Poisson point process. So these off-diagonal terms, which depend on the sign of x minus xj, in other words, whether the sensor is to the left or to the right of that contact point, when we take the expectation of those, they will produce 0. So next slide, please. We can then, and you just need to calculate the diagonal terms, and these, the formula in the first bullet, expectation of sigma 1 over sigma j squared, these are, it's lambda, so lambda is the intensity of the Poisson process. In other words, it's the average number of sensors per unit length in this one-dimensional problem. So the diagonal terms in the Fisher information matrix are lambda times this integral of 1 over sigma of x squared. So then if we model the performance of the sensors by some way in which sigma of x squared increases with distance, we have done this here by having some sigma naught, which is the root mean square error at close range, and then some length scale L, which measures the length scale over which the root mean square error increases to be significant multiples of sigma naught. The details of what function you should actually use there will be much more properly modeled by what Alistair describes later. So then, next slide, please. We can then calculate what the Cramer-Rao lower bound is on estimating the variance of our contact position. And it's this, there's a numerical constant and then sigma naught squared over lambda L. So it shows quantitatively just the sort of things we'd expect, that to get a low variance, you need accurate sensors, small sigma naught, you need large density, large lambda, and you need large L, longer range sensors. And in fact, more precisely, this product, lambda L, which you see in the denominator of the expression there, if we go on to the next slide, then the expected number of sensors within L of a given point in this one-dimensional Poisson process is just 2 lambda L. So the lambda L is proportional to the number of sensors within the range L of the contact point. So the form above is more or less what you'd expect. It's a sort of sigma naught squared over n kind of formula. We should note also that we would expect a similar approach to work in 2 or 3 dimensions. Those quantities that were the sign of x minus xj, just plus or minus 1, would be replaced by unit normal vectors in the higher dimensional space, but they would still average to 0 in the off-diagonal terms of that Fisher information matrix. So apart from some scaling factors that depend on whether you're in 2 or 3 dimensions, we expect that this analysis would press on through. That shows we can at least make a start on this question, but what are the caveats? Next slide, please. So the caveats are many and various, and this is just a start on some of them. You'll see it's predicated on assuming Gaussian noise and calculating a Cramer-Rao lower bound. Neither of these are very good assumptions. There are going to be errors in the timing that are not Gaussian. There's also quite a bit of literature going back over quite a time on better lower bounds than the Cramer-Rao bound, which I've listed some of those here. I think we should press on. So can we go to the next slide, please? So in thinking about the noise question, there are, a sensor generally picks up things that might come under at least 5 categories, those listed here. There's data from the contact we're interested in, there's data from other contacts, there's clutter like multipath echoes of the contact we want, there's noise, and there's missing data. And any algorithm that's going to resolve such a situation must cope with these effects. And the way they interact and combine will vary a lot depending on the problem. So suggests something that Catherine said about one of the other challenges yesterday, that perhaps the question is too general to have a generic answer. So can we go on to the next slide, please? If we have sensors that say they provide good data with probability p, but provide no data at all with probability 1 minus p, then that's not such a bad situation. You just need the number of sensors that are providing good data to be sufficiently large, and it just has a binomial distribution, and you'd be in a good situation. But if the bad sensors that with probability 1 minus p, instead of providing no data, if they provide noise data derived from some unknown distribution, then there are all kinds of errors that will arise. I think for time, perhaps we better go on to the next slide and the next one. And we wanted to think whether there's some problem in the sort of middle ground where we can say that it's it's specific enough to do some analysis, but representative enough to give some insights into the larger problem. So we wondered about something like this. Suppose we have n sensors that are trying to detect the time of arrival of a signal emitted from unknown point x at time t. And suppose with probability p, you have a sensor that reports the arrival time with just a Gaussian error, but with probability 1 minus p, it reports a random time drawn from some other distribution which might be unknown, and maybe the value of p is unknown. So finding the fundamental limits on estimating x would be a question that you could begin to address mathematically, and it would shed light perhaps on how those limits depend on p and on the noise distribution and so on. I think this needs discussing with DSTL to know whether this is a model problem that would attempt to explore some of the things they're interested in, or whether it would need modifying, or whether there would be different areas that they want to explore. This really is just comparing true signal plus noise to the sort of true signal plus missing data question. If we wanted to go into multipath, then this would need modifying in some ways. So I think next slide, and then this is where we hand over to Alistair.
Okay, thank you very much. So I should say that I think the form of this is due to Gabriella, so I'm just presenting it. So it's really about going into a bit more detail about how the sensors behave, in particular relating the timing error to the signal to noise ratio, which in turn can be related to the distance from the source based on some path loss factor. We've determined that it depends on the signal that's being sent, in particular upon its bandwidth, and we actually end up in fact, I think this was came from a number of references that we found to have a fairly simple dependence in the equation at the bottom. So it's inversely proportional to SINR, signal to interference plus noise ratio, and this factor beta squared. Next slide, please. And if you look at that expression for beta squared, think about it a bit, it turns out to be a sort of normalized bandwidth, or squared bandwidth, which of course makes the expression on the previous page dimensionally correct. It has dimensions of time squared. So that again is relatively simple and much as you'd expect, but you can see it depends on the spectrum of the signal as it's received. So we can then use the Cramer-Rao bound to go back and calculate, well, this is based on the Cramer-Rao bound, which then can be used to go back and calculate the location error in the manner that David's just mentioned. But it assumes a perfect sensor, etc. Next slide, please. So we need to think in a bit more detail about the characteristics of the antennas, the sensors and the channel, in particular on the spectrum of the received signal. So that's one aspect. Better move on. Next slide, please. Then, of course, there are all sorts of other transfer functions in the sensor, such as phase noise, etc. And we need, in principle, to begin to characterize those as well. It was certainly something we understood DSTL were particularly interested in. So we would need much more detail to examine that. Next slide, please. Right, so then very quickly, we talked about information theory was mentioned right at the start. We did have a brief discussion, but we didn't really develop it. But I, in particular, and in this discussion, felt that there is a potential approach to it that can perhaps more general, produce a more general and abstract approach that isn't so related to the specific algorithms that we've been discussing up to now. So one line of attack is to analyze the system as a single input, multiple output, a SIMO system. And we can derive an overall likelihood function, which again isn't dependent on the algorithm. Of course, this isn't totally unrelated to the Cramer-Rao-bound approach anyway. The other thing would be to analyze the performance of the sensors in terms of information flow through them. And that we could then use to characterize the multipath noise, etc., and find sort of bottlenecks to the overall system performance, which again was one thing DSTL seemed particularly interested in. And also enables us to think about combining information from different sensors of different qualities. We also mentioned rate distortion theory, which may also have a role. Next slide, and I think I hand back to Tony.
Okay, thanks, Alistair and David indeed. So this really is our last slide, and is some summary of the next steps, some of which we are highlighted along the journey there. So yes, extending this toy problem to more complicated cases is the normal modelling journey. So that would seem correct. There's other, if we stick with geolocation, there are other ways of doing that, not just time of arrival. And we mentioned non-Gaussian noise, extensions to 2D and 3D, and then the effect that the SINR timing error has on the spatial error. Then, as Alistair was saying, there's the whole transfer functions approach to specific sensors, multipath modelling. That seems to be a sort of hot topic at the moment. And finally, getting somewhere with this other way of approaching things. So, yeah, I think that's where we got to. So, thank you all.
Thank you very, very much. Excellent. Sounds like you've got through a lot of work this week. So we've got a few minutes for questions. According to my schedule, we should be kicking off with challenge 2 at 10:05. So yes, so some questions, please. But before we do that, it would be really good to get a view from a DSTL person or a PA person. I know James Matthews from PA was in there, in that group. So I don't know if James or another DSTL colleague would like to give some sort of feedback on this.
So is Joe on the call at the moment? No.
Yeah, got there eventually.
Had
lots of IT issues this morning. Yeah, so from my point of view, basically we've done quite a lot of work in DSTL looking at theoretical limits, and it's really important for more so for our procurement process than anything. So understanding the art of the possible, how close we are to those limits, where we're going in the future, that kind of thing. And it was really good to see these guys in the group have a look and listen to what we've done already. And everything that they've done and listed looks like it would be a very welcome addition to the work that we've already carried out. So, I mean, it'd be really interesting to see if there was scope for sort of joint papers in the area, that kind of thing. If we could, I'm going to try and endeavour to share some of the theoretical limit work that we've done already in DSCL with these guys, because I think that was a bit of an issue at the start there. We were unable to share that work, so it took a while to sort of explain the problem a bit more coherently, but we soon got rolling with it. So I think if we at DSCL could look at sharing that report with the necessary people and then taking those suggestions forward into some joint work, I think we're particularly interested in things like the components within the system and how that affects overall performance, as has been said, but also incorporating those kind of potentially non-Gaussian errors and things like that into the sort of multi-path geolocation limits in an urban environment. So that was really good to see. And yeah, if Alistair can crack out that information theoretic side, that would be amazing. But yeah, all of those challenges, all of that future work to me looks like it would be really useful.
That's fantastic feedback. Thank you. Do any of the group team have a quick response to that?
Well, to say thank you very much to James and Joe for interacting with us over these last few days, which have been great and very helpful.
No, and I think it's really heartening to hear that although there are obviously going to be obstacles because of the security issues with sharing information, that there is great scope here for future joint work and collaboration. So that's exactly what we're wanting to achieve here. So that's brilliant. Does anyone have any other questions they'd like to ask the team? Okay, if there's no questions, then I guess, is there someone just popping up for a question here? John? No? Okay, so perhaps if we move on to the second challenge, and that is, if I can find my pages, understanding the fundamental limits of information fusion. Now, I know this was involved Alan Champneys. There are a number of other people, so I don't know who's going to present on this. So is this Alan kicking off with this presentation?
Sorry, it wasn't allowing me to unmute myself. One of the things about not being blessed with multiple monitors during lockdown is doing things that require two screens are remarkably difficult. Now I can't get rid of this control panel. Hopefully it'll go on its own. That's interesting. When I share, it doesn't want to go full screen. All right, we won't be full screen. Okay, so this was challenge 2, which were the fundamental limits of data fusion. We had a really good mix of expertise in the room, which I thought was fantastic. We had some experts in information theory, some people in machine learning, artificial intelligence, people in image processing, both from an EE and a mathematics point of view. And I think we all said we learned a lot just from talking to each other, even if what we've done on this problem is not actually helpful. So this is essentially the batting order, the running. I want to very briefly recall the problem, refine the question, and then we have 3 approaches to this, broadly speaking. Approach 1, I shall pass over to Catherine Mitchell, who will talk about the notion of inverse problems. Then I'll pass over to Ollie Johnson, who will talk about some fundamental information theory ideas, and then pass over to Martha Lewis, who will talk about data fusion, and then a summary, which will be me again. So if you recall the scenario, rather than sort of the problem in the abstract, the scenario we were given is imagine a lost child. And we also started talking about Catherine's lost dog at some point. And imagining you have some data, and some of that data may be a very different kind. It may be data about past behavior. It may be completely different bandwidth. It may be a GPS sort of location data, or it may be a huge video file. And the fundamental error in those data, the fundamental uncertainty in those data may be different. And each of your sensors that's picking up that data fundamentally has its own error correction and has a mathematical model in it. And the question is, essentially, if I go to the next slide, well, we thought we managed to tease out 3 kind of levels of question. The levels of question might be, there is a lost child with different sources of numerical mathematical information, which may be incomplete or incompatible. Can we find the child? Problem B is we have completely different data sources, visual, audio, conceptual, and need to combine them. There may be behavior data, there may be categorical data, but the question is still, where is the child? And there may be some issues with where and how we combine that data at bottom level or top level. And then there's question C, where not only is the data ill-defined and multi-sourcing, we don't know how even to describe the data, that's problem B. Problem C is we don't know how to describe the question mathematically. Is the child safe? Are they lost? Are they a threat? A model is needed to obtain the input and to interpret the output. We decided this was interesting, but given the limited time, this was too vague and difficult to tackle now. So the steer from DSTL was, can we focus on problem B? There are lots of algorithms to deal with problem A, and they're context specific, etc. But problem B is the tricky one when data is coming from different sources and data has different types, and we don't know how to model the data, let alone or to process the data in a unified format. So, as with all presentations, this is going to be presented in some logical order, imagining that we had a massive brainstorm and then did a down select. Of course, it doesn't happen like that. Out of a sort of a melee of soup of ideas, there are the ones that we're going to present to you. But the other thing that happened throughout the week, really, or the 4 days, was a discussion of all the mathematical approaches that there are. And this is, just a subset of some. There are algorithm level approaches to data fusion, model updating using adaptive filters, Kalman filters, or 3D VAR, 4D CAR. Sorry, there's a nice typo, isn't there? 4D VAR used in weather forecasting and meteorology, etc. There are lots of optimization or inversion problems. Essentially, many of these things can be thought of as inverse problems. Essentially, we're trying to learn. We've got some operator acting on data, and all we can see is the output of that operator, and we want to learn what is the data that it's really operating on. And depending on the context, there are lots of algorithms, and there's also this idea of minimum mean square error as a way of sort of estimating error. There's also the whole area of AI and machine learning, and the concept of reinforcement learning is a very useful one here. And it can be used with both numerical and categorical data, categorical data like blue or afraid or raining, as well as, numerical data. And then we talked a lot about an awful lot depends on having a good Bayesian prior. We'll find that in a minute. Prior knowledge of your data is important, and a lot of methods seem to go wrong about us. They rely on an implicit assumption about the prior in your data. Some image processing algorithms, for example, you can get optimal bounds, but we don't really know what a prior space of all images is. But actually, recently, deep neural networks are learning Bayesian priors, and that's something that might be interesting. And then there are ideas of particle filters, ensembles of models. There's a notion of random finite set tracking and probability hypothesis density filters that are used in tracking problems. And then there's more modern ideas in topological data analysis and graph-based learning, which is for things that are really not linear problems. But at some level, at bottom level, there is some Bayesian approach. We have some prediction of where the target is going to be. We have some prediction of what the data is like, and we have some prediction of what the error is in the data. So the refined mathematical question from DSTL was, given a mathematical approach X and a data set Y, what are the limits on our output and result? So this, by the way, was the audio-visual tracking that came from Wenwu in Surrey. And there's quite a lot of detailed algorithmics there. And this idea of finite random set, sorry, I forget the name of it now that I put on the previous slide. There's a lot we can learn there, but I think this is mostly in the problem A space. But there's a lot we can learn about how to represent error in this scenario. But I now hand over to Catherine to talk about what we know about inverse problems coming from questions or applied examples like tomography.
Thank you, Alan. So I'm going to take everybody now to a very specific example so we can really focus in on something that, that is the real problem. If you look at the right-hand side, you can see I've drawn a little diagram there, which is starts at location A and goes to location Z, and it represents a road, the dotted line, which is going over a hill. And the problem that we're given then is that there has been a sighting of the child on the road. So that's all we know to start with. And so the challenge we have immediately is, how do we translate from the fact that there's been a sighting of the child on the road to something that is actually mathematical? And so on the left-hand side there, we've got the kind of thinking process as to how we translate into pseudo-mathematics from a descriptive event. So we can say that we have a set of locations, which are little boxes on the right-hand side, which is a set of possible locations the child might be. And if we set up the problem like that, we can effectively say immediately it's an inverse problem. And so the inverse problem is such that the sum of all the locations along that path are equally likely, as far as we know, because there has been a sighting, but we haven't been given the specific location. And so that's what the pseudo equation on the left-hand side represents there. The integral of or the summation of the discrete points along the path is equal to the sighting. And we can't solve it because all we know is the child still was along the path. There is no solution to that problem at the moment, no unique solution. But if we're given a bit more information that we can use, and the example of the information I'm going to say here is, let's just say, for example, that we know that children don't like to be at the top of hills, they like to be in the valleys. Then that immediately tells us our assumption that allows us in the inverse problem language to regularize the problem. And so what we can then do is to say that the most likely locations for the child are at the bottom of the hill, i.e. close to location A or location Z, and much less likely to be at the top of the hill. So the challenges that we have there are, how do we actually move from descriptive information into mathematical information? How do we translate our observations into something that can be used in a model? And how to regularize the inversion, as in when we don't have enough information, it's an underdetermined inversion. How do we actually solve it, and how do we bring that information in? And the two key points I just wanted to make from this really simple example is that there are two critical ways you can go wrong with this problem, even this incredibly simple problem put in front of us now. The first way you can go wrong is by actually not realizing how to regularize the inversion, so not knowing that the child doesn't like to be at the top of the hill, so not being able to bring in the right regularization. If you don't do that, you can't really make any solution. The other way that you can go wrong is picking the wrong mathematics, and this is absolutely key, and it is very specific to the type of problem we're solving. So in this case, if we picked a mathematical solution that said we have to have one location in the solution, we wouldn't be able to pick between location A and location Z, because we would simply be saying that they are equally likely. They're both at the bottom of the hill. We don't have anything to make the decision between them. And so our best answer in this case, and this is coming back to the original question, what are the limits to our data fusion? Our best answer in this case is two answers, either location A and location Z. Our worst answer, which some mathematics could give us, would be the child's at the top of the hill. Because if we're forced to one location, we might say on average they're in the middle. And I'll pass back to Alan now.
And straight on to Ollie. Next slide. Sorry.
Okay, no worries. Right, so I wanted to talk about some information theory approaches to this, because we're talking about fundamental limits. I'm an information theorist. As far as I'm concerned, these are at least a set of fundamental limits. So I think it's fair to say that a lot of what we've done so far is playing with toy problems, but I don't think you should think that these toy problems are the limit of the use of this model. It maybe just sort of illustrates what you can do. So something, for example, I sort of very early on said, well, obviously the best thing is if the observations that we see are independent. I mean, clearly that seems obvious. And actually it turns out that's not true. And so by playing with the toy model, we realized that my intuition was actually completely wrong. So here's an example where this intuition isn't true. So we have a very simple setting. We have X as a random variable on the real line. And what we see is we see two noisy observations of it. So we see Z1, which is X with noise N1, Z2, which is X with noise N2, and N1 and N2 are bivariate normal. So, like I say, my guess was that it would be, the best case would be that if the bivariate normal was independent. And actually that's not true. So what it turns out is that the sort of a way to think about this is to calculate the mutual information. So the mutual information is essentially the channel capacity. It tells us how much information Z1 and Z2, how much information these outputs of the sensors have about the thing that we care about. And the nice thing about this very simple toy case is that there is an explicit formula for this. In this case, there is an explicit formula that you can write down, and that it's basically the log of the ratio of some determinants. And so in this case, it turns out that this independent intuition is completely wrong, that actually the worst case is when N1 and N2 are identical. So if N1 and N2 are the same, then clearly there's no more information in the second one than there is in the first one. And so you only have one observation. But actually something very, very close to that is best. So the best case is when N1 is a multiple of N2. If N1 and N2 are proportional, then actually you can perfectly recover X just taking a linear combination, and the mutual information is infinite. Now, obviously, all the engineers are sitting here in the room saying, oh, well, yes, that's obvious. That's just a linear filter, you know, Gaussian, yada, yada. But the point is that this is a more general framework than that, that this information theory, the mutual information, you can calculate in a lot more settings than this, or you can bound it in a lot more settings than this. So it's at this stage, it's just a sort of check that the models kind of coincide and that the answers coincide. Okay, next slide, Alan. Right. So another kind of pitch for information theory is that actually we can decide what measurements to take. So in other words, we can decide where to put our sensors or how to do it. So Yanis, who I'm not sure whether is in this room or not at the moment, has this very interesting example where there are these two different settings. So there's an X that you care about, and there are two versions of how you get Z1 and Z2, how you get these noisy measures. So one is that X kind of splits in half, that you get Y1 and Y2 that are independent noisy versions of X, and then those are put through noise. And the second is that you take X, you get a single noisy version of it, and then those have noise added to them. And so the question is, which of those is better? So the question is, in some sense, you know, which of those carries the most information? And you may have a belief one way or the other, and the answer is we don't know. Well, we don't know in general because it depends. So actually, there are, for different choices of P and Q, the answer will be different. And so again, it seems like, you know, your obvious intuition as to, oh, this is definitely how the world should work, isn't necessarily valid in this case. Okay, next slide. So sort of general pitch for why information theory is valid here, why it's a useful approach. So firstly, these quantities crop up all over the place, that things like mutual information, relative entropy, Fisher information, when you start talking about any kind of estimation, detection, classification problems, these are the things that turn up in the bounds. Like I said already, in simple cases like the Gaussian case, particularly because the density has a particular form, the theory kind of coincides with the linear filters, and so what we recover is essentially the Cramer-Rao lower bound. But my sense is that the information theory framework is richer, it's more general. It doesn't need that these variables be the same kind. I mean, it could be that Z1 was binary, Z2 was real. We were playing with an example that was like this yesterday, and then I got sucked away into other things, and so we didn't quite finish it. But it definitely works in that framework too. And the other thing that I think is interesting about information theory is it can tell us how well we can do however smart we are. So in other words, that there's this idea of a converse result. And specifically, it can give us a bound that says, no matter how good a job you do, no matter how smart an algorithm you come up with, then you can't do better than this. This is a sort of fundamental bound on the performance of inference for a particular model, regardless of the algorithm. And that's really important, because that's telling us what we want to know. It's telling us that we can't do better than this, however smart we are. There's a couple of other points as well that, I've been doing these toy examples where we assume that we know all the distributions, we know everything, but actually there are techniques in information theory that tell us what to do if that's not the case. Obviously, it's not realistic that is the case. So how do we choose an optimal distribution, even when we don't have full information? And there's a point here about information fusion, which I think relates to what we're going to come on to next, which is that in mutual information, there are these properties like the chain rule that say how mutual information changes at different stages when you take summaries. So if you take summaries early versus if you take summaries late, mutual information can guide you on the right sort of strategies to use there. Okay, next slide.
Okay,
Right,
so this is over to Martha, I believe.
Managed to unmute myself. Okay, so yes, so the one question we then wanted to look at is at what point should you kind of put your data together and analyze it? So is it better to kind of take your data and put it together into one long vector, or to kind of process them separately and then combine them? And this can obviously happen in various different ways. You could process various different parts of it at different times. And how can we tell and at what point does it matter or not? And the last point on the slide there says also that we still haven't decided how to actually translate kind of concepts, the kind of information that we might get from, let's say, the mother of the lost child, that the lost child has a black coat on. We still need to be able to translate these concepts into the data to be fused. And we're not going to talk about that quite yet, but in the next slide, we go on to just a very, to kind of get a handle on these questions. We looked at a very, very simple example. So in this toy problem, we assume that we just have data from just one location at one time from two different sensors. And suppose we've got these two different data types, each represented by real valued vectors. Next slide. So what can we do with those two different vectors? We can process them separately, and here these boxes F and G correspond to two different classifiers. So on the left, box F takes in data, takes in a vector of data and gives you back a probability, let's say, of seeing a black coat given that vector. And on the right hand side here, you've got a class probabilities, sorry, a vector of data, and gives you back a probability of, for example, hearing a child's voice, given that that value. And each of those classifiers is trained on different data sets. So one set of vectors in the visual domain, one set of vectors in the audio domain. Now, the other thing you could do is you could take those two different vectors and put them into one box H, which then gives you back the same two probabilities. So we're still just working with processing the same vectors to get the exact same information. And here, this classifier is then trained with labeled data that's paired. So the visual data kind of corresponds to the audio data in that they're taken from the same time point. And so then the question that we wanted to investigate using this framework is that what are then the differences between the individual components of the output of H and the outputs of F and G? And so when is it more appropriate to use individual classifiers F and G that just take into account the data on their own rather than a joint classifier H? So in the joint classifier H can take in, can use information about the audio black coat in the visual environment. So like it says there, there's no general answer yet, but we can look at these extreme cases. So we can look at when the conditional probabilities are independent and start to work out what the differences are there. And we can also look at when they're mutually exclusive. And I think we found there that actually then we get some expressions that kind of don't make sense at all. So there we want to, that's also something to look into. Next slide. And it seems to depend on the nature of kind of false positives. So for example, if we have a black coat and a high-pitched voice, are we seeing the black-coated child that we wanted to find, or are we actually seeing a cat? And I think the question there is that this answer depends on these Bayesian priors for prediction. So where are you going to get these Bayesian priors from? Well, if we can analyze the data set nicely, if we know kind of how we're training the classifier, then this can inform us about the kind of priors that we're using there. And it's also got to do with the uncertainty in the sensors as well. Back to Alan, I believe.
Yeah, perfect. Just a couple of minutes from me, 2 slides. So recall our question was, given a mathematical approach X and a data set Y, what are the fundamental limits? I think we've come up with 2 further refined sub-questions, which are, what is the value of the next piece of information? And are we better fusing the data before or after processing it? At what level should we fuse? And it seems in practice, it all depends on our prior knowledge of the mutual information in the data. And in fact, I think our 2 toy approaches are actually converging, one using information theory, the other sort of probability theory and machine learning. It is about these Bayesian priors of the mutual information. So a more nuanced question might be, actually, given a set of algorithms that we might use and a set of data sets that we're trying to fuse and our current set of Bayesian priors, then what is the fundamental limit on our ability to predict? So some possible next steps. We need to keep going with these toy examples. Actually, they're converging. So maybe merging the thinking that we've had in these 3 different toy examples and perhaps bring in something slightly more realistic about the data. In inverse problems, there's an awful lot of use of heuristics and regularization. Can we bring that into these frameworks? Can we say, well, you know, a heuristic is like another kind of Bayesian prior. Is that better than a different kind of Bayesian prior? And we can also try and analyze more complex problems. For example, these audio-visual tracking algorithms, there are some pretty smart algorithms out there, but it would be good to see whether they've been thought of, and we don't know enough of the literature from this fundamental information theoretic and Bayesian probabilistic framework. In inverse problems, as sort of Catherine was alluding to, I think, there are problems with underdetermined problems and overdetermined problems. Can we bring that into the data somehow, into this framework somehow? And then can we think about these nonlinear models? You know, the information theoretic thing allows for really quite general classifiers and quite general models, and perhaps think about links to reinforcement learning and other AI approaches to learning priors. What are the limits there? You know, there's a conference this week, in fact, I believe, at the University of Bath on the mathematics of deep learning. Can we get some handle into making some estimates if there is an AI in the loop? And then actually, perhaps the fundamental question is not what's our limit on detection, but what's our fundamental limit on the ability to make a good decision? So you think of what Catherine was saying about, given the data, the best thing we can convey is either there or there, not a best estimate of a crisp point and a nice little ellipse around it with an error bar. And there are ways of communicating uncertainty and representing the data so that a good decision is made based on the sort of, you know, fuzzy logic or degree of uncertainty, the orange region in an Italian flag rather than the green or red region. So that's where we got to. I think the general feeling was this is an extremely hard problem and we're only just scratching the surface of it. And ultimately it's so context dependent, but perhaps we've outlined some ways in which you can think about those problems in different contexts.
So thank you very, very much, all of you. There's obviously a lot of work gone on there. So thank you to Alan, Catherine, Ollie and Martha for presenting that back. So before we go to questions, could I ask for a sort of end user perspective? I think Richard Dakin was in on that group. I don't know if Richard would like to comment, or somebody else perhaps.
Yeah, Richard Dakin here. There may be others in DSTL who were more involved in setting the challenge, so just leave it open to anybody else that might want to comment.
Any comments from any DSTL colleagues?
Hello, can you hear me? This is Alistair Hunter from DSTL.
Yes, we can.
Hello, thank you very much, everyone, for that presentation. Yeah, you talked about doing these type of problems and taking them forward, and I'd encourage you to do that, and also about but you're trying to do a sort of general approach. So if you wanted to apply it to a kind of a specific area, you might get drawn into, you want to avoid getting drawn in too much to the specifics of that area, while you want to be able to still use that as an exemplification of the general approaches. One point that one speaker made about the decision, the outcome of it, certainly from the DSTL perspective, is that a military user very much wants to be able to make a decision. So that point about being able to express the uncertainties to help make a decision. So that's perfectly correct about being able to say, well, it's either you know, the left or the right, but not necessarily in the middle. So that's definitely something I'd encourage.
I could say that we had some very useful input from your colleagues Paul Thomas and Stuart Scarfield, who really helped steer us, as did Richard Dakin and Rich Green as well. But at key moments, Stuart and Paul were really helpful, because we seem to be getting lost in the fog of trying to do everything.
It's always better to do some smaller thing well than everything badly.
That's really, really useful feedback. Thank you very much. Do we have any more questions from any of our other participants before we move on to Challenge 3? No? Okay. Right.
There's a question in the chat. Is that for us about countermeasures?
Hi there. Sorry, it's Steve Moore, MOD here. So it's just a question from me. I was just So it was really good stuff. But yeah, I always also try and think from the other perspective about how we defeat. So just interesting whether your insights into how you're solving the problem, did that come up with any potential ways to actually counter your way to solve it?
I
would say we didn't particularly get that far yet, but I think the framework could work. I mean, so in general, what we've been looking at is a fairly sort of static analysis in a lot of cases, the sort of toy problems. There is a framework of information theory that can cope with these kind of adaptive things. There's something called directed information theory, which basically looks at what you know at a particular time, you know, how much information is there at a particular time. So I think that those tools would work in a more adaptive setting. I've certainly used that in the past. But yeah, we had 3 days, so not there yet.
No, that's cool. It's great work. So no problem.
Thank you, Oliver, and thank you, Stephen, for posting that question. And another quick one before we move on, or?
Yeah, hello. Hi, this is Geordie Barr from DST. I have to apologise because I've only arrived right at the end, so I may have missed quite a lot. I was interested in the inclusion of priors, which is a really good idea. But what does a good prior look like? You know, there's a certain amount of black magic involved in devising these things. I'm wondering if there's any insight on what constitutes a good prior as opposed to one that isn't particularly helpful.
I don't know if Zara's on this call. I mean, she was our sort of machine learning person. I mean, one of the things that we got to was that actually, or anyone else in the group, not necessarily her, that actually in a machine learning environment, you know, if you're taking lots of these measurements, you know, it's a different problem if you've never seen a lost child before. So you don't know anything, and then you just have to guess a prior. But if you've actually, if your business is detecting lost children, then you will have a lot of information that you can have learned. So I don't know if any of my group members want to comment on that.
So I just wanted to say that although it's not perfect, what you can at least do is if you can at least kind of analyze what the labels are and so on in that training data, and that will give you a sense of kind of how you're training the system that you're using, and that can kind of feed into a prior there.
So yeah, I'll just add to that. I think adding the human in the loop with some active learning and having some transfer learning approaches as well, with learning from similar domains when the child is lost, but with different sensors for collecting. So if we learn from this domain and add this incrementally to the whole algorithm, so that will help in adapting the model incrementally in real time. So there are some approaches in machine learning that can help us to change whatever we have learned before from the training data. It doesn't have to be static all the time.
So I think I'd like to move on, please, if we may. I guess if anyone else has any other burning questions, they can post it in the chat. So moving on to challenge 3, optimization of sensor location. Now that was one which involved Bill Lionheart, amongst others. So I don't know if Bill's going to kick off with that presentation or one of the other team is going to.
Hi. Yeah, I hope Will Handley's ready to do the first part, and then Justin Ward is all ready to do the second part. Will, are you there?
So I am here, but I'm also happy for Justin to lead on this because a lot of my stuff is stuff that was discussed yesterday. So
cool. Justin, do you want to share your screen with those slides rather than me, because my Zoom just kicked me out a moment ago. So
yes, that's fine. Let me just. Okay, it might be Will, if you've got some general information about the problem and your approach, I think I was planning on going after you to
okay, I'll kick off then. That's not a problem.
So you maybe go ahead now that I'm looking at it. I'll stop sharing. Here you go.
Okay, so some of these slides were shown yesterday, but for the benefit of the recording, there's also been some updates to the figures, and I'll sort of therefore go through this possibly in a little less rapid time than I did yesterday, which was quite brief. But basically what we're looking at here was a problem with several different aspects to it, but fundamentally the problem stated was that you need to place transmitters, or you need to place sensors in an urban environment that in theory has reflections and things like that, and non-trivial constraints of limited access as to where you can put these sensors. And you need to detect a transmitter somewhere in that sort of environment. Maybe using reflecting signals, maybe using direct signals, but in general, you have some complicated model. So we kind of initially started with this kind of very rough sketch, and with a few prompts from DSTL, it was established that whilst there was an element to solving this where you had dynamically moving sensors in the urban environment, a good start was to begin assuming that it's static, i.e. you want to solve for the best thing, and if you can solve for that fast enough, you could then adapt that to be a dynamic thing. But basically this is sort of a problem where you need to maximize coverage whilst minimizing cost, and where maximizing coverage is quite a technical term. So in this first diagram, in our first pass through this on Tuesday and Wednesday, we defined coverage as just any region that was that had line of sight to one sensor. And so that kind of image there of the mathematical problem here, when we sort of move from our toy example to something that's still a toy example, but a bit more quantitative. And you kind of here, just for reference, the rectangles would be, we're looking down on a cityscape, the rectangles are buildings, and the blue region might be a waterfront. And basically we want to sort of place sensors, which each individually will have a line of sight profile that might look something like this. And as you place more than one sensor, you will get regions that might, for example, have double coverage here or single coverage there. And as you move, so in general, this problem is stated could be viewed as a 2n dimensional optimization problem, where n is the number of sensors, and you have sort of two coordinates here. There may, of course, also be a height and a third dimension, which would be, you could either view as a three-dimensional problem, or you could view as a two-dimensional problem with an additional function or complicated way in which these sensors profiles depend on X and Y. So yeah, the problem is, it is stated in this very general way, is maximize coverage, theta, where coverage is in this case defined as single coverage, subject to non-linear constraints, e.g. sensors must be on roofs, or if they're on roads can only be in certain places, and things like that. So in this diagram we have sort of, I'll write down the percentage of coverage as being 73% there. So in the kind of one sort of, if you like, subset of our work was just saying, why don't we forward model the entire problem instead of sort of trying to sort of discretize it, or we just kind of write down the full problem in a toy problem and solve that as best we can. And that's one of the things that we did using a non-linear, non-convex optimization tool that's capable of sort of navigating these multimodal spaces that are generally quite challenging. And of course, once you do that, if the problem is non-convex, any guarantees you have are the problem has multiple minima, and often minima may not be points. So things like asking, have we found the best answer, become less relevant, even though you do have guarantees of finding minima to within a given resolution using these techniques. You may not even want to be finding the absolute best one, because if it, in a multi-objective framework, you may desire a suboptimal coverage if it also reduces cost, or if that coverage is more robust to small changes in the locations of sensors. The other thing to note is that this is high dimensional, and that if you were to brute force grid search this becomes prohibitively expensive for n=1 or for high resolutions. There's a nasty sort of quadratic or exponential scaling depending on how you phrase this. So in the first pass through, I sort of we applied a nested sampling algorithm called Polycore that we applied previously in the previous workshop to a very different Bayesian related problem. And when you do that, you find that if you have n=1, that's where you should put the sensor. And Justin will talk about the fact that in this case, for this single coverage case, you also can solve the problem exactly. and these do tend to agree. N equals 2, you find that you place one sensor in the same location, you get a good coverage here, but in the jump to N equals 3, you find that you actually get quite a big reconfiguration of the system when finding this global optimum. And in doing from N equals 2 to N equals 3, you get sort of a jump from sort of 93% to 98%, and that being quite different coverage. Of course, when you solve for this using an ensemble related approach, you get multiple solutions. So there are other solutions which are slightly less good coverage, which looked more similar to the previous one. And then N equals 4 is approaching 100% coverage within the sort of discretization limit of the integral that I was doing here. And just a few more points about sort of ensemble-based optimizations in this way. Whenever you do an ensemble-based optimization using something like sorry, I thought I had a list there. Whenever you do an ensemble-based optimization, you're left with a set of solutions at the end, and this set of solutions can be useful for many reasons. One thing which I think DSTL said they were interested in is it's very useful for analyzing the stability or robustness of solutions. So here I take some other good solutions that come out of this ensemble, and you can see that as I flip between them, you find that in this, these two are rather important, but these two can be moved around relatively freely. So you don't need to care too much about how you place those, providing you just stick them on this building, because it's clear that this orange one is just covering this small region here, and this green one, providing it has an access to this corridor, gets a pretty good view of that. So that's worth bearing in mind, that this is useful for both getting multiple solutions that you could hand over to a human decision maker who may be able to select the best one using another much harder to encode mathematical criteria. It might be useful for re-optimizing over alternative objective functions. So it might be that this is a cheaper one to do because you have different regulatory constraints, or that you couldn't actually do this in practice because it's the wrong kind of wall to put the sensor on. And yeah, as I said before, this is very useful for analyzing stability and error bars, because you effectively get something like a Bayesian posterior out of this. So after that, this is where we go on to a new bit that I didn't discuss yesterday in the brief presentation. We realized that we needed to make this problem a little bit more realistic, and that in actual fact, because we're trying to detect a transmitter, you're not just looking for covering everything by at least one region. Because in fact, in this case, what you'd really want is, for example, this is one of the only regions here where you have a triangulation between the blue sensor, the red sensor, and the green sensor. So here you would get, if you were assuming you were searching with sensors that only had yes or no detections, the only bit where you'd be able to pinpoint anybody would be in this crossed over region. Whereas if, for example, you had transmitters that had some element of timing information, that would mean you'd be sort of having two sensors measuring that would give you a lot more information. So as a proxy for sort of getting for a proof of concept, we basically worked on the model where you make a detection of a transmitter if two sensors detect it. So these would be sensors with some kind of either direction or timing information that might give you additional that might give you enough information to pinpoint where it is. And in this case here, if you were to put these two sensors here, you can see that they get a good sort of paired detection in this region, and also paired detection in this region, because there's sort of a line of sight to both there, but not here because you're in the shadow of that building from that one, and here because you're in the shadow of that building. And importantly, one of us spotted that it was rather pertinent that we wanted to avoid something where, for example, if you put two sensors directly next to one another, those would then get paired views of everything. So we also applied a constraint that all sensors must be at least 15 degrees apart. Now, to be clear, this is very much a proof of concept approach. This is not a final decision. The correct answer here would be to have a much more sophisticated sensitivity model, where basically you are trying to sort of encode a continuous function that tells you how accurate an answer you'd get given the locations of these sensors, and you'd be optimizing over that. So, but again, one of the things I would like to emphasize is that because we're forward modeling the problem from the beginning in this approach, it's very general. So the extension from single coverage to double coverage here was relatively, was a very small change in the code and very little difference in runtime for doing this. So whilst you can get guarantees in stripped down versions of the problem, this way here, because you've taken the hit of forward modeling at the start, any additional extensions become a lot easier to sort of both comprehend and to implement. So anyway, it turns out that this is the n equals 2 best solution in this case. And if you look at n equals 3, you get to here, which kind of makes sense, although it's interesting that it chooses not to put anything on the central building, because you think a human probably would think that would be the optimum place for paired sensor detection. As you move to 4, you start to get some interesting effects here. So for example, just so everybody's on the same page here, you can see that this region here is mostly detected by these 3 sensors, and this region here can be seen by both the orange and the green sensor, and this region, this corridor here, can be seen by the green and red, and similarly this region here by blue and green. And as we move to the optimum solution for 5, you get some quite fun effects, like for example, this region, despite the fact that it has line of sight to blue and orange, can't be seen because of our 15 degrees constraint. And you can see that you get this rather interesting region here just before that where the red sensor has line of sight, and this gives you 99% coverage. So this is quite a fine-tuned solution. If you sort of go further down the distribution, you start to see some other solutions that are similarly good, but slightly less, have slightly less sort of fine-tuned regions like this. In terms of further work on this model, again, as I said, this is very extendable. The first thing, the most important thing to do would be to start incorporating things like reflections and a realistic, fast-paced ray tracing using something that might be optimized on a GPU. And again, the main thing is our proof of principle sort of paired detection model should be replaced by a continuous metric. And we did spend some time talking about that in the context of general measurement models and sort of what the next steps would be in that that are in the report, I believe. And of course, this could we assumed here all the sensors were the same, but this could be just as easily extended to having different types of sensors. So it might be that some are simple yes, no detection sensors because they're cheaper, and others might have directional ranging because that, you know, it might make sense to have a directional sensor that can detect where something has come from on the top of a building like this. And of course, you would also possibly want to extend this to dynamic updating for mobile sensors. In terms of somebody has just posted in the chat whether this can be extended to 3D to take into account of building height, and the answer is yes, very much so. This is a 2D sort of simple model. It depends on whether you want to mathematically model 3D as just an extra scalar function on 2D, as in height is an extra scalar function on that, or whether you want to go for a full 3D modeling, which of course would be the more appropriate one. And yes, this would be very extendable. The dimensionality really comes from, in this case, you're optimizing over a 10-dimensional space, because this here, the jump to 15 is not particularly large for these kind of techniques. Okay, I think that's all I have to say on this portion of the work. Justin, I think that's enough lead up for you to start talking about our work on linear programming and that kind of stuff, unless anybody has any other questions they want to ask at this point.
Perfect. That's just what I needed. Let's see. I'm trying to reshare this thing. Okay, there we are. So one concern about the continuous optimization was that in general, the objective function you're going to get for this thing, the coverage objective is non-convex, and we figure probably Will's approach does a great job of handling that. We wanted to get a more, to somehow quantify exactly what the optimal solution would look like. So one way to cope with the non-convexity is to actually discretize the problem down into a sort of combinatorial discrete problem. So you can imagine just placing a grid in the city, some chosen side length, and imagining that the locations you want to detect have to be, you know, intersections on this grid. And then also discretizing the set of possible places you can put sensors. So once you've done this, there are some mathematical approaches that will give you the optimal solution. Of course, here now you're working on a discrete problem instead of a continuous problem. But notice for this to make sense, instead of convexity, if you want, you can think we really only need that the objective be more or less smooth, which seems a little more realistic, or a little less to ask. So once you've done this, you can imagine you have a set of discrete locations that you want to detect your transmitter from. and a set of discrete locations you can place your sensors. And then you can write down these two optimization problems, depending on what you're after. So one over here is the set cover problem. So here, the requirement is that every single location be covered by at least one sensor. And that happens right here in the program. So these are just the integer programs, if you want, for these two kind of standard problems. And so again, this one you have every potential target locations observed, and now your objective is you want to accomplish this by using as few sensors as possible. So, and the other problem, which could also be useful to solve, is essentially the dual of this problem. It's called maximum coverage. And here the hard requirement is on the sensors. So you've only got K sensors to work with, let's say. And you want to, your objective then is now to reveal as much of the landscape as possible. So you want to cover as many target locations as possible. So this is sort of what Will was showing earlier, was this maximum coverage. How good can we do with 2, 3, 4 sensors? So from a mathematical perspective, worst case sort of theory, both of these problems are NP hard to solve exactly, and they're actually both hard to even get a guarantee for in reasonable time. But one of the heuristics people use in practice is just this greedy heuristic, which is probably one of the first things you'd try if you'd never seen the problem before, which is just, I need to place these sensors, so I'm going to place them one at a time. And, the first sensor, the thing that makes sense is to put it in the place that reveals as many locations as possible. And then when you place the second one, you just put that in the place that reveals as many new locations as possible. And you just keep doing that until, well, in the case of maximum coverage, you put out K sensors. Or in the case of set cover, you keep going until eventually you've revealed all the locations. So what we know is that this simple heuristic for the maximum coverage problem is actually guaranteed to give you about 63% of the optimal coverage. So in the absolute worst kind of adversarial cityscape you can come up with, you'll still get within some constant factor of the best possible coverage. Now in set cover, things are a little bit different. So it ends up, if you do the greedy thing here, you can actually end up using log n more sensors than optimal, where n is the number of locations. So for example, if you've discretized your space into say 1,000 points, I guess let's take logs with base 10 because there's some constant hidden in there anyway, then this says, maybe you could expect to use 3 times as many sensors as you had to. So this is a little bit scary. So all this reams of math I've got up here, I'll talk about really briefly. I don't think this probably isn't really reams, just a few lines, but so you can formulate these as an integer linear programming problem. And the thing that makes it hard is this integrality constraint, right? That you can only place or not place a sensor. So what we did to kind of get a feeling for the problem in the discrete setting is we implemented both of these. So first we used Will's forward modeling to give us the coverage regions for each potential sensor location. And then he could actually generate a set of potential locations, and for each one, essentially an incidence matrix or detection matrix that shows, this sensor detects these locations. And that gives you your matrix A here. And once you've got that, you can encode this in an integer program and feed it to some commercial solvers. So I just tested it with Gurobi. And the question, of course, is that we know that these problems are hard to solve in the worst case. So for this instance, where I think we discretized to over 1,000 locations and over 1,000 possible sensor placements, what's the actual performance for this solver? And what we got is here is the plots you get. So I ran, the top here is the integer programming solver, and you can see it puts down one sensor here and 2, 3, 4. And the optimum it could do with 4 sensors in this discretized problem. So again, this is going to be probably, I think it is a little worse than Will's solution because of the discretization. But if you really only could place sensors at those locations, and you only cared about detection at those discrete locations, then we can get with 4 sensors up to, I think this is about 98.8% coverage. And I'll talk about running time on the next slide. But it was okay for this problem, even given the fairly fine discretization, but I suspect it's not going to scale well. So one thing to look at is, okay, we have these worst case bounds on greedy, but these instances are probably not going to be like the really highly structured worst case instances. So what does greedy do on this? So we ran the simple greedy algorithm on the same thing. You can see here, this makes sense because if you've got one sensor to place, then the greedy choice is actually the best, right? You're just going to put that at the place that reveals the most locations. And actually for 2 sensors, the greedy choice, the greedy is again doing exactly the same thing as the optimum. And also for 3. So where things get interesting, and this is sort of what Will was pointing out, is when you get to 4, you can see what's happened. We've got slightly less coverage from the greedy algorithm, and the reason is because it's placed this blue, orange, and green sensor, and because of the way the algorithm works, those are fixed. So now it's going to add one more sensor to it. And once those have been fixed, the best addition is this kind of strange red cone here. Whereas the optimum in this scenario is actually, now that you've got a 4th sensor to work with, you want to reconfigure all your sensors because you can use that 4th one to make up for some lost coverage if you move another one. So this is just a simple example to show that, in fact, the greedy is not going to necessarily do the best thing, but if you look at the numbers here, so here's the kind of interesting K=4 case. So the optimal discrete solution here ended up covering 98.8% of the space with 4 sensors, and the solver took about 6 seconds to run. So with these integer programming solvers, even if you've got, so if you add some more exotic aspects to the problem, then we saw the runtime goes way up. But what you can do is, because of the way the algorithm works, you can say run for, if you get a hard real-time constraint, like 15 seconds, you could say run the solver for 15 seconds, and then tell me what you've got, and it will give you both the solution and bound on the solution. So it will say, here's my solution, and I guarantee this is within 10% of optimal. So what's interesting is greedy, despite the kind of bad guarantee, actually got almost to the optimum, right? It's covering 96.3% of the space. And what's really interesting is it's running on the discrete problem in 8 milliseconds. So greedy in general, we know scales up really well, essentially linear in the size of the discretization and the number of sensors you want to place. Here, probably it's doing especially well because in our instance, you don't need that many sensors to get really high coverage in the first place. I would suspect if you need, say, 100 sensors before you start to get significant coverage, probably this gap is going to get bigger, but also this runtime is going to get bigger. So for the set cover problem, we ran the same experiments and noticed that here the optimal is you can actually cover every single location in the city with 6 sensors. And that we could find in about a little less than 1 second with Gurobi's integer programming solver, whereas greedy is actually going to use 8 sensors to do the same job. But again, right, the runtime is super low. And intuitively, this is just because of the same issue I showed you on the last slide, which is that the greedy algorithm can make a kind of myopic decision at the beginning that ends up locking it into a configuration that doesn't allow it to fully utilize all 6 sensors. So it probably at the very end, it needed to put 2 little sensors down to cover tiny little holes in its solution. So that's the basics of the discrete approach. In terms of recommendations and further work, let me go back to this. So the nice thing about the integer programming is that it's extremely flexible. So if you have some non-homogeneous set of sensors, right, you have different costs, it's easy to just incorporate your different sensor costs into the objective here or into this constraint here. If your locations have different coverage requirements, you can plug that in. Probably you could put in the angle coverage, but that's going to be tricky. So the integer programming formulation is extremely kind of robust to variance of the problem, but it could take a really long time to run. Like, so here we have guarantees on the solution quality, but no guarantees on the runtime. Now for greedy, you've got guarantees on the runtime and some guarantees on the solution quality, but not so great. And also, as soon as you start to say things like a location is covered by has to be covered by 2 different sensors, most of these guarantees go away. So some future work would be to try and actually see, can the greedy heuristic be modified to be able to take into account these more realistic coverage scenarios like Will mentioned. Maybe you can still get a guarantee. Maybe there's some better explanation for why, in this case, the greedy algorithm is doing almost optimally. And if you could quantify that, like what do the instances we're actually solving look like, then you could potentially get some stronger guarantees here as well. So I guess the last thing that I think is interesting is notice what we've done really is Will's got this great kind of forward model of the environment that takes all the physics and the geometry into account. And what we've done here is basically used that to generate a discrete instance. And then once we've got this discrete instance, which is really just this, this incidence matrix A, we forgot about all the structure of the problem and just threw it into kind of a bog standard combinatorial optimization routine. So probably a better approach would be to remove that separation and actually think, is there some kind of fast optimization algorithm that, with guarantees ideally, that can operate kind of directly in this physical realm instead of throwing away all that information before you run it. So I think we're running a little bit long, so I'll end there. If anybody has any other questions, I'm happy to take them. Thanks.
Thank you very much, Justin, Will and Bill, for that very interesting and excellent presentation. Yeah, I'd really like to move on to the next presentation in 5 minutes. So if I can initially ask if there is an end user DSTL or PA opinion on this. I think Emma Bowley was in this group, so I don't know who'd like to say something from DSTL or PA.
Yeah, I was in the group. I don't know, Joe, would you like to say a bit about this, as I think it overlaps with your area as well?
Yeah, absolutely. So yeah, I mean, we're definitely interested in both approaches and the direction of travel here. We've got ray tracing software, full 3D ray tracing software, and our current methodology is basically like brute forcing it for all locations. So any way we can take down the number of computations would be really amazing. Potential way forward could be to potentially provide the academics with channel impulse response models for a city broken down by grid, or something like that, to see if the linear programming could come up with a full 3D optimized solution. Another thing of interest definitely is the robustness. So the model and reality are never probably going to match up. You're not going to know what the surfaces are made of. So being able to win those impulse responses, because we can give you sort of surface and time time of flight and things like that, you know, change the material or variance on the material so that we end up with a more complex but perhaps robust solution when our knowledge is kind of fuzzy. That would be really interesting. And another avenue of work which this seems sort of key for would be if we can incorporate the kind of time frequency aspect as well as the spatial aspect into the optimization problem. So for example, if your sensor had 2 bands of interest, a high frequency and a low frequency band, and it couldn't cover both at the same time, how could you optimize your sensor placement, and what sensing strategy would you use? So what sensor would sense what frequency at what time to get the most global coverage or whatever goal would be required. But no, really interesting stuff. Very good to see the output in this. So yeah, that's it from me, I guess.
Thanks, Joe. Of course, we mentioned a lot of those things in the report as well as future work. So yeah.
Brilliant. I'll have a look at that. Thank you.
Thank you all. I don't know if we've got that much more time on this, but if everyone's been looking at the chat, there's been a few things going in. Ollie Gage has asked about different approaches if you add in constraints of being unable to place sensors in specific locations. Alistair Burr has made a comment about can approaches readily be extended to include reflections, and Stephen Moore has also made a comment. So there's a number of others. So I don't know if we've really got time to address all of those. I don't know if
we've already started answering them. Sorry, we've already started answering them in the chat, and we can carry on doing that if you like.
Okay. Do we want to perhaps just quickly cover one of them? Perhaps Stephen Moore's from an end user perspective.
Just for me, it was just the what I'm trying to look ahead is I know there's a big thing about quantum computing. Maybe it's a great white elephant. Who knows? Park that for the moment. I'm trying to think about how we get ourselves kind of ready to exploit, or what the benefits that advanced computing could give us. It looked to me like what you were arguing there partly was also actually investing in some of that computer, or the exploitation of computing might lead us to other savings. So it's just from the other perspective.
Can I just jump in to answer, make a general point? It's Mike Hobson here. The thing that Will presented, the thing to take away is that you have a forward model. That forward model you can really make as complicated or as intricate as you like. That comes with a computational burden that can be addressed through various techniques. But once you have that forward model, you then need to navigate a parameter space that is typically high dimensional, multimodal, contains lots of thin curving degeneracies, etc. And the key to what Will presented, although it's only, it's not working in a very complicated context in just what he presented in a day's worth of work, is that there are methods that exist to navigate those spaces, and they're ensemble optimization methods. So at the end, you get this robustness automatically. So the key message to take away is there are techniques that can navigate these complicated optimization problems in an ensemble fashion, irrespective of the nature of the forward modeling, which can be as computationally sophisticated as you can make it. That's the takeaway from what Will did.
Happy with that. I think it's I'm always, where I'm trying to come from is that if we ignore the computing power limitations, actually it means that we can then invest and look at those optimization techniques you talked about, and look at that very complex space, and not be scared of going into that type of S&T. So I guess that's why my great white hope of quantum computing might solve that problem, but let's not wait for it to solve it. Let's crack on and do all the other S&T for it.
You don't need quantum computing. Normal CPU computing isn't that expensive compared to putting sensors on the ground, right? It's like 1 pence per hour if you do it sort of effectively.
That's why the swap issues as well. But Project Quantum comes with swap issues as well. So yeah, that's cool.
Will solve his problem in a very short amount of time on a laptop. I mean, that's something that he didn't mention as well. So I mean, all the stuff that Will showed was on a laptop and ran very quickly. So it's worth bearing in mind.
Okay, thank you all very much. Thank you, Michael, for your contribution as well. And to the team 3 people for pulling all that together, excellent. So moving swiftly on to challenge 4, soldier systems. Now, I think Eddie Wilson was involved with that, with a number of others. So I don't know if Eddie's going to kick off, or one of the other team.
Yeah, that's right, Jane, it's me. I'm just going to try and work out if I can share the presentation, or if my my computer will crash. Can you see that?
Yes, we can. Oh, well, I can see it, Eddie.
Well, I'll give the talk just to you, Jane. So this was challenge 4. This was the soldier systems challenge. I'll explain what that means in a minute. We had a small but beautiful and fully engaged team, and many of the people on that slide are going to speak in our slot that follows. Now, first catch. Oh, there we go. That worked. So what was the challenge? You should imagine that there is a group of soldiers. Well, they're a team, and they might equally be firefighters. They might be robots. So let's just call them agents. And they're moving through some environment. I'll talk more about that in a second. and they're trying to get to a particular place together to perform what we call their primary objective. So their primary objective as a constraint is that they arrive together in some box in two-dimensional space in a given time window. But these agents, they're also equipped with various sensors, and as they move through the environment performing their primary task, they have a secondary task, which is to do some sensing, which might be imaging, tracking, or locating some hidden transmitters. Now, when we came to this, we saw this almost completely through the lens of optimization and operations research, because clearly there's some kind of trade-off between the primary and secondary objective, and you can think about either weighting them or perhaps incorporating the primary objective as a hard constraint. So we were completely down the operations research and optimization track in terms of our way of thinking about this problem. The second thing is we then talked a little bit about the nature of the environment that the agents pass through. And it seemed to us there was, at least for learning purposes, it was useful to have a dichotomy of two completely different types of environment. So for example, your agents might be moving through the floor of a building, or they might be moving through a dense urban environment. And then they are going to be constrained to moving along corridors or possibly the street plan of a city. And that to us seemed very much like they are moving along the edges of a graph. And so we thought that one approach would be to think of this very much from a discrete perspective and view it as some kind of graph search problem. And we'll talk about that in the first half of the talk. And then there's a second setting, which you might call a rural setting, where the agents are completely free to move in two-dimensional space. There may be some obstructions, but of course the state space is continuous, and it seems useful to separate that out as a completely different approach, because then you have calculus methods and so on available to you. So that was the dichotomy. Now let me talk a little bit more about the secondary task. Of course, there could be all kinds of secondary sensing tasks, but we decided to specialize on the case where the agents attempt to localize a single unknown radio frequency transmitter. And the assumption is, again, assumptions. We'll assume the agents each have a sensor. The sensors are identical. They're omnidirectional. And all they do is measure the received signal strength or some metric of received signal strength from that unknown hidden transmitter. We're going to assume all kinds of other ideal things which should be relaxed in future. For now, we are assuming completely instantaneous information sharing between the agents so that they have a common view of the state of the world at any point. We have not addressed the latency aspect of this question as set on the first day of the workshop. So the key is, just actually as in problem one, you have to think about models of received signal strength. And we spent some time looking at what was in the literature for that. Of course, there's an enormous comms electrical engineering literature about received signal strength and path loss. We came across this thing called the Cost-Hatter model. You really don't want to see the formula, and also it doesn't fit on the slide, so that was my LaTeX trick to get past that problem. The issue is, in all those very, very complicated path loss formulae, which somehow try to summarize the aggregate effect of obstructions such as buildings and so on, they're deterministic. And that's absolutely no good for us, because if the soldiers are able to make deterministic measurements of our SSI, in principle, they can go to 3 locations and then triangulate and perfectly locate the transmitter. So it's essential that you have some model of the randomness in received signal strength. And we talked quite a bit about that randomness. There is a lot out there, for example, in terms of fading models, which gives you randomness in time in signals. But actually, we couldn't find a lot, and I defer to the wider electrical engineering group that are listening into this talk. We couldn't find very much literature about random spatial variations in path loss to model unknown complex cluttered environments. And that essentially is what you need to do this kind of challenge properly. But for our purposes, that path loss is a random variable. It's going to be a random variable whose mean decreases in the distance from the transmitter. And the key is that the dispersion models things like unknown obstructions or reflections in the radio environment. So that's all about the secondary objective and characteristics of the radio environment. So to kick you off with the sort of first version of the discrete formulation, and then I'll be handing you to Jari, who will show you some implementation and computation. This is what we've got. It's a graph. The agents might be starting either at the same or different nodes on this graph. They're going to traverse through the graph. They're all going to try and get to the same node within a given time window. We call that the primary task. That's the blue square. But at the same time, they're trying to locate this hidden transmitter, which here is this green rectangle. It could be at one of the nodes for simplicity. You can do things like assuming each agent moves at a constant speed. And what we were keen to do is go just entirely discrete and put this in a discrete event framework. And the natural way to do that is to view that a setup where everything happens when agents reach nodes. There's a finite time for an agent to traverse a node, and all of the communication and sensing updates happen when agents arrive at nodes. So that was a convenient simplification, but one which can be relaxed as you go forward. We're assuming agents have perfect instantaneous communication. There's no problems with the channel. Of course, that's not realistic, but it's a starting point. And the other key assumption is we are assuming in what we've done so far that the agents have global knowledge of the graph that they're traversing. There is a set of extra problems with an enormous literature around them, where the agents would also, as part of their primary objective, be trying to discover the graph that they are passing through. And we've discussed during the week all sorts of heuristics, how the agents make their turning decisions, where in such a way, essentially combining heuristics which represent new node discovery with finding shortest paths and making local decisions based on direction, which would somehow give that graph exploration flavor to the problem as well. But this is, I think, is a good point to hand to you, Jari.
Thanks, Eddie. If you could go to the next slide, please. Great, thank you. So we coded up a little toy problem to sort of get a feel for this discrete formulation. And we've made a number of simplifying assumptions just so this was practical code up in a day or two. But a lot of these can be relatively straightforwardly relaxed in this discrete framework, which is one of its strengths. So we're assuming that agents move one node per time period and sense at each node once they arrive at a node. And we're assuming that both the primary and secondary targets are located at specific nodes on the graph. And we move agents to a neighboring node based on a score that we assign to that node. And to calculate this score, we take two pieces of information into account in this simplified model. The first one is the RSSI. So either if we've already visited an adjacent node where the agent is considering moving to, if that RSSI has already been measured, or alternatively, we can estimate the RSSI. So for example, we might interpolate the value of the RSSI for a node we're interested in moving towards based on other RSSI values that we've already sensed nearby. And the other piece of information we use to determine which node to move to is the distance to the primary target, specifically 1 over the distance. And this serves as a way to guide the agents towards their primary objective. And then we assign each node a score, which is essentially a weighted combination of these two pieces of information, and we can adjust the weight to persuade the agents to either spend more time looking for the secondary target or focus more on heading towards the primary target. And in order to decide whether an agent should move to an adjacent node, we sort of randomize this procedure. So we take a random draw from the distribution of scores for all the adjacent nodes. So essentially you can think of that as a weighted dice. So we sort of roll a weighted dice, and then based on the weights, which are given by these two pieces of information, we decide which adjacent node an agent should move to. And finally, we have this hard constraint that the agents have to reach the primary target at the end of some given time period. And so the way we do this is when we look at moving to a neighboring node, we compute the shortest path from the adjacent node and the target node and decide whether we have enough time left to move to that node. And if we don't, then we assign that adjacent node a score of 0 and the agent doesn't move there. And in this way, we can constrain the process such that the agents always end up at the primary target at the end of the time period. Next slide, please. So, for example, let's suppose we have 3 agents in the bottom left corner of this graph, green, red, and purple. And let's suppose that the primary target, our ultimate destination, is located in the top right corner of the graph, and that the secondary target, that's the transmitter we're trying to sense and locate, let's suppose that's located in the top left corner of the graph. And let's suppose that the agents have 8 turns to reach the primary target while simultaneously searching for the secondary target. Next slide, please. So our starting position is like this. The agents are in the bottom left corner. Next slide, please. So now after one step, the agents have moved. So notice, because we are doing this, there is a certain degree of randomness. There is a small chance of moving to nodes which have both low RSSI and are quite far away from our primary target. So in this case, you can see the green agent has moved to the bottom left corner, just the randomness we've introduced. Next slide, please. Now we can see that the red agent has started to sense the secondary target in the top left corner is being drawn towards that, while both the green and purple agents, which are currently overlapping in the bottom right here, are heading more towards the primary target. Next slide, please. So you can see the red agent has now reached the secondary target. The green agent is moving towards the primary. Purple has moved back. And again, you can see red agents now moved past the secondary target, and all agents are starting to converge towards the primary target because we're running out of time. You can see red agents has just had time to go back and verify that the secondary target is there. And now we really are out of time, so all agents have to move to the top right corner and head towards the primary target, which they do at the end of the time period.
Okay, thanks, Yari. And I should just say that, I mean, that's just one implementation of a very wide variety of ideas we've had around the various search heuristics. So I'd now like to pass to David, who will talk about the continuous branch of the problem.
Good morning. So my name's David Bourne from Heriot-Watt. So yeah, now I'm going to focus on the continuous problem, where our agents are in a more rural environment, like Eddie said, say they're moving through some fields or a desert. And the sort of use case suggested by Stuart from DSTL was, the question is, what's the optimal search pattern of agents in an open environment? And as before, our primary objective is to reach a target on the other side of the mission zone, so on the other side of the battlefield, say, in a minimal time or distance. And the secondary objective is to scan the environment to gain information about some secondary target. And the assumptions are the same as before. So it's a 2D environment, meaning our agents are people or vehicles, not drones. And we're assuming that the agents and sensors are identical. Okay, so here's a simple mathematical model. So we suppose we have n agents, and xi of t is the position of agent I at time t. And this is a point in a two-dimensional set omega, which is representing our desert or our fields. And we assume that the initial location and the final location of the agents are specified. So capital T is the mission length, and yeah, x of 0, the initial location, and x of t are given. And the other parameters in the model, we have Vmax, that's the maximum speed our agents can move. This could be a constant, or it could be spatially dependent, so it could depend upon the environment. Do we have marshes? Do we have rivers to cross, quicksand? And another parameter is rho. This is a probability distribution on our domain, which represents our prior knowledge of the secondary target. So it could be we know nothing at all about where the secondary target is. In that case, rho could just be the uniform distribution. Or if we have some guess about where it is, then it could, say, be a normal distribution peaked around our best guess. And finally, there's a parameter in the model, lambda, and this weights the importance of the primary objective compared to the secondary objective. Again, as Eddie said, we're viewing this as a optimization problem. In the model here, the goal is to minimize an objective function of the following form. So our objective function E of x, it's got two terms. The first term represents the primary objective. And so here we want to minimize the total distance traveled by our agents. And the second term represents the secondary objective. And this you can think of as we're trying to sample the environments. Our agents are trying to sample the environment, or at least to sample rho. And this is a sampling error. I feel like it's the distance between the agents and the environment. So that's it in words, and then maybe I'll just describe the equation briefly. Yeah, so the first term is really just, it's the length of the agent's paths times this weighting parameter lambda, giving the importance of the primary mission. And the second term is some distance. So this is some distance between two probability distributions, one representing our knowledge of the secondary targets, and one representing where the agents are. And the choice of distance is a modeling assumption, and this is where you could encode information about the sensors and the signal strength. Okay, and here's, so we did a simple example, minimizing E numerically. For this, we do a time discretization. There's no spatial discretization. And we did some numerical optimization in MATLAB, just constrained optimization. And for this simple example, the parameter values are, so our mission zone, our battlefield, or if you like, it's just a square field or a square desert, omega. And we assume we know nothing about, no prior knowledge of where the secondary target is. So rho is just a uniform distribution, sort of equal chance of secondary targets anywhere. And for this simple example, our choice of distance, this distance between the probability measures, we chose the 2-Wasserstein distance. So the reason is this is it's a very standard distance people use between probability distributions. We had the software to compute it, and it does encode some strength, in some sense, the fact that the signal strength decreases with distance. And then here are some results. So this is an example of two agents moving in a square field. So if we look at, or here are two examples. If we look at the left example, so in green, the green circles on the bottom are the initial positions of the agents, and the red circles at the top are the final positions. If we were just interested in the primary target, these would be straight lines to minimize the distance. But because we have this secondary objective to scan the region, then instead of moving in the shortest path straight lines, our agents tend towards the center of the square. And then you see a similar picture, the right picture again. The agents don't move in straight lines, but they just sample the environment better. They deviate towards the center. And then here's a similar picture with 3 agents. Again, you see them doing a bit more exploring than just going for the shortest path. And the amount of exploring you do depends upon this parameter lambda, the weighting between the two terms. And you can see this in the next slide. So this is just very simple, one agent, and it's the effect of this weighting. So the bigger the lambda, the more important the primary mission. So on the left-hand side, lambda is 10, you essentially move in a straight line, your one agent. In the right-hand side, lambda is 1, and your agent goes further into the center of the domain. So the best place for him to be would be the very center. That's the best sampling of the uniform distribution by a single Dirac mass. So that's why he moves there. And finally, just briefly, is a very simple example of an obstacle. So the left picture is there's no obstacle. The agent tries to move in a more or less straight line because lambda is very large. In the right picture, we have an obstacle, and the agent deviates around that. So we can include obstacles here too.
Okay, so I'm going to invite Jörg and Yunpeng, I think, to join us.
Thank you.
So this is now going to be an attempt to present a conclusion and next steps as a kind of unprepared cabaret act. Well, what have we done? I think we've got these two completely different views of the problem. They have many common elements, but they are mathematically sort of entirely separate streams, and we can make progress in both of them. I suppose there's lots to do. For example, do you want to talk a bit about, David, about updating in the second problem, perhaps?
Mm-hmm. Yeah, so that's a good point. So what I showed you, the entire path of the agents were determined in advance. But we've also considered, but not implemented, a dynamic version where you can update the paths as your agents gather information on the environment. So what you could do here, a simple way would be to, if you get some more information about the environment, then you solve the optimization problem again with a new initial condition, so the new location of the agents, and by updating row your knowledge about the secondary target. So you can imagine you solve the optimization problem once, and when you've got some more information, you solve it again, and you can do this and update the paths.
Thanks. Jörg, would you like to say something about the general setting of these problems within the wider context of standard operations research problems?
Yeah, so basically we formulated the whole problem as a multitude of optimization problems, either fully in the discrete domain or fully in the continuous domain. One can also imagine mixed models where we have a mixture of continuous and discrete variables here, say a mixed urban and rural environment. We did not do that, we ran out of time. But basically, this seems to be the right way forward, given that we found what I would say is a very, very flexible way to model the problem, with various possibilities to extend it in the form of, well, more or less classical operational research optimization problems.
Mm-hmm. Jori, I was going to bring you in on the next slide, maybe to talk about various ways of generalizing heuristics. So should we go there?
Mm-hmm.
So, there's prototypical code, and I suppose there's a whole bunch of various assumptions which should be relaxed as you move towards production systems. And Jori, what do you think about some of the heuristics in your search and how they would generalize for some of these cases where I'm hovering my hand?
Absolutely. So the discrete problem that I talked through can be easily generalized to cases where we have, for example, several emitters, several secondary targets. It's a straightforward extension. Also agents with varying speed, also straightforward. We can also model imperfect communication between agents. So agents can just use their best estimates of RSSI if they haven't received any communication. And also we can extend this, and this is a little bit more involved, to graphs where we don't know the entire network, the entire graph in advance, and we're discovering parts of the graph as we go through. So these are the sort of things that can be, and of course many more can be done within the discrete framework.
So thanks, Jori. I can't see Yunpeng on the call. But
yeah, I'm here.
Okay, hi Yunpeng. Would you like to say something about the other learning approaches?
Yeah, sure. As Jörg just mentioned, also as we relax assumptions, it would be useful for us to learn the environment, because one assumption that we can make is that we assume that we don't have perfect knowledge of the environment. And so it will be desirable for agents to of the state. And so this boils down to simultaneous tracking and learning. And for state tracking, particle filters are a standard tool, as also Challenge 2 team has mentioned. But particle filters basically assume that you have perfect knowledge of the environment, because you assume that you know the dynamic model, so you know what is dynamics, so state dynamics, and also you know the measurement model, so you know what is the relationship between the observation and your state. So recently there's a development on differentiable particle filter, which basically use neural networks to learn the dynamics and also the measurement model. So that is something that's interesting to explore to address this issue. But standard approach basically assumes that you have ground truth information of the state variable for you to learn those neural network parameters. And one interesting for us to look at is to develop some unsupervised learning approach. Basically, we can try to maximize some pseudo likelihood of the observation, so we don't need to have the ground truth state information as we learn those neural network parameters. And one side benefit of this approach is that we may also be able to predict observations in new and unknown places for us to, for agents to make more informed planning. And so this can be achieved by a component of that differentiable particle filtering framework, where you use generative models such as generative adversarial networks to learn to simulate new observations and then compare it to the true observations you make, and then learn a model to predict the observations. So those are some interesting directions that we can go.
But in terms of implementation, far too difficult to do this week, right? Okay. That's. I think we're done, Jane.
Thank you, Eddie. Thanks, because we probably do need to move on to the next challenge now. But it looks like you've done so much work. It's incredibly impressive. So thank you to Eddie and the rest of the team for presenting that back to us. It would be really good to see if we can get just a quick response and from an end user perspective. I don't know if Emma or Rob would like to do that.
Jane, Stuart here. I was one of the SMEs on the from DSTL in Challenge 4, so I can provide a bit of context. Rob as well was heavily involved on the PA side, so he can give us his perspective on the day. So from my perspective, really fantastic discussions, really good team. Obviously, work presented today really shows the benefit and what came out of that. Particularly impressed by the efforts of the team to generate some of the practical models you saw, some of the graphs that were generated in the presentation. So as the team goes sort of above and beyond in the time they had to try and actually implement some of these approaches, particularly to David and Yari for coding those, but obviously the wider team for really pushing and providing information to enable us to do that in the time we had, which is really impressive. Certainly for me, it's really interesting here from a defence perspective to understand how some of these techniques might help us better use the information we have. I mean, defence has a much broader challenge of how do we use all the data we might be able to gather? If we do fit sensors on all our platforms, all our agents, how do we use that data? And in this particular scenario, it was really useful to understand how we might guide military forces and security forces to conduct their mission through, while at the same time enabling them to conduct a secondary mission, but essentially reducing the cognitive burden on them. So rather than them having to understand the full environment around them, make those decisions about where they should go next, these kind of approaches might give us a way to guide them as to say, if you could just go that direction, that might be a preferential from the secondary objective perspective. And if that reduces the burden on them, then that's a really opportune thing to explore for the future. Certainly the expansion of the ideas here to dynamic scenarios, and we mentioned the sort of scenarios where you're growing the graph as you traverse it, are really powerful and certainly quite applicable in the military domain, where we may believe we know the map in front of us, but obviously roadblocks or vehicles breaking down or adverse reaction may force us to take a different path, and the fact that these models can potentially be expanded to include that is very useful for application in the military domain. So really useful. That's it for me. Just to say thanks to the whole team for your efforts. Really useful week, and hopefully really useful. And yeah, welcome any comments in the time we have for the rest of the audience. Thank you.
Thank you.
Brilliant, thank you.
Thank you for that detailed feedback as well, Stuart. Unless anyone's got a really burning question, I would like to move on to challenge 5 because we're running out of time. I noticed that there are a couple of more comments here from Fumi and also from David Allwright. So I would draw everyone's attention to that quickly. Stuart, were you wanting to say something else? No, I think you've just still got your mic on. What I would say before we rapidly move on to the last challenge feedback is that all you'll have seen from the programme that the Zoom rooms remain open. So obviously group 1 go into room 1, group 2, room 2, etc. So that people, when we finished up, people will have the opportunity to pop into those rooms and see some of the people who talk to some of the people who've worked on those challenges. So just to remind you of that. So then moving on to challenge 5, which is fundamental limits of a single photon detector. There are a number of people involved in that, including Sean Holman, Oliver Dawn, Nick Polyodorides, etc. So I'm not sure which one of you is going to kick off.
It's me, Kurt Langfeld. I'm kicking off.
Thank you, Kurt.
Okay, I try to share my screen. Okay, this is our group here. We had a wide range of expertise, including tomography, sensor imaging, and computational simulations modeling, and our presentation will reflect that. So the presentation is on HackMD if you want to look at it. I scroll through as I go along. So channel 5, fundamental limits of a single photon detector. Let me just remind you what the problem is. Here we have a laser which illuminates a scene. The laser gets reflected from the object of interest, and then on the way to the object and back from the object, there's a lot of scattering which blurs the image. And the question is, what can we learn about the object of interest, and how do we take into account, how do we get rid of the blurring? And that is the task. We wanted to just talk about fundamental limits, but of course we couldn't avoid to talk about how we could make it better as well. So let me start with a very simple mathematical model to set the scene, and then we move on to more evolved techniques. So first of all, why does scattering blur images, and how do we use cuts in the time of flight? The one element which is new by just shining a torch on a scene, we have additional information. The photons which come out of the laser, we know the time when they reach the target, and we can use this additional information to maybe reconstruct a 3D vision of the object. And that's a new element from just shining light on an object. So let me just remind you where blurring comes from. So this is the laser here. A photon will be emitted, it scatters off a corner, let's say here, comes back and makes an image on the screen here. And that is what we want. There's no interference from a screen which maybe scatter the signal back on the way there and back. This is the real image we want to see. But of course, what happens is one of the photons scatters off in a different direction, hits an obscuring screen, and then might find its way back to the detector. That would mean for the observer, we get a second image of the corner, which would be here. And that simply means that basically we have a blur of the corner from here to here. And that is something which we want to get rid of. And then of course, it's how can we do this? You intuitively notice here that this is the shortest path we can have, the shortest time of flight. And this path here has a much longer time of flight. So if we put a cut on the time of flight, we just might get rid of the additional trajectory, which we don't want, and then we get a much de-blurred image. And that's the basic idea what's going on here. So we first did a simple model to illustrate and to find limits. So here you have one scattering screen, one obscuring screen. This is the laser. This is the receiving array. The screen is 10 meters away from the laser, and you have a metallic plate behind the screen, which is the object of interest. And then we need to model scattering. Whenever a photon hits the scattering screen, there is a certain probability distribution in the change of direction of travel. These are just the details. You can look later on it if you want. It has a forward characteristics of scattering, but anything can be used here, and there will be a better choice in later on in the talk. So what can you get? So let's remove the screen and just look at it. So we did a trajectory is 10 million photons, and without screen, you just see this image here of the metallic plate in the background. And you see already we lose a lot of photons on the way there without scattering already, because we have to illuminate the scene. Only around 90,000 photons make it back. And if you take a histogram of the time of flight, you see that. It's interesting to see this is 30 meters over sea, this where everything starts. It's the shortest possible path, and then it goes up, and it's just a little bit away from 30, you know, and that's the distribution, which is purely geometrically. Now, if we put the screen in, you get a completely different picture. This is if you put the screen in. First of all, only 80,000 photons come back because some of them get scattered away from the screen. 80,000 of the 10 million photons, and you get a rather blurred image of what you want to have. The interesting stuff is here on the right side. You get sort of, if you look at the histogram of the time of flight, you see a change in scales. This is 20 meters over sea up to 35 meters over sea, and you see two peaks. You see one peak here, and you see a peak here, and that peak comes from photons which are directly scattered back from the screen, which don't make it back the screen at all. So this is a highly opaque system. Parameters were chosen in such a way. This is a highly opaque system, and you see we lose most of the photons from the initial screen. And you think about it, if you shine a torch on a piece of paper, you want to illuminate what's behind the paper, you just see a white paper. And that is what we see here. So we are interested in this stuff here. So first of all, you could now say, okay, I throw away every photon which comes earlier than, let's say, 28 over C, and then still you get much less photons then, but you're looking at the photons who at least reach the target. And still it's still blurred because you get a broad distribution here. This is 30 meters over C. Basically, you are interested in these early photons which don't undergo any scattering. So we can now apply cuts here as well. So and that is what happened then. So this is the picture without any cut on the time of flight. You get this blurred image you've seen before, and then we only include photons which come in between 30 and 31 meters over C. So you see you get rid of some of the scattering, and then if you cut further, if you only include photons between 30 and 30.3 over C, you're down to 169 photons only out of 10 million, but you see you can start recovering the image you want to have. So what are the fundamental limits of that? First of all, if you have a wide cut, basically you get a lot of blurring, so that's not interesting. That might be sort of coming close. Is this optimal is a question. And then of course, if you cut too much, you lose the photons, and then this is not a representation of the image anymore. So how can we sort of mathematically quantify that a little bit? Okay, you could just say we have photons I from 1 to n, and they make speckles on the screen or in the area at positions xi and yi, and then what you could treat this as random events and calculate the average, which would give you the center of mass of this figure, but more interesting, calculate the standard deviation, which gives roughly the size of the object of interest. So you can do this for the unobscured object, but then you can, of course, do this for these images as well. And then you can just do a least square difference as a measure of overlap of the images. This is just a very crude idea. Of course, you can use higher cumulants for Fourier modes, and doing that the infinite amount of ideas. But you know what you get now is simply a picture of what's happening here. This is again the three pictures: a wide window of time of flight, maybe the optimum, and that's a small window. And this is now how the measure comes back. So delta is the size of the interval, the time interval you're cutting. So it's between 30 and 30 plus delta. And this is what you see. There is an optimum here. So basically what happens if the delta is too small, this is then this scenario here. So you lose photons and the overlap becomes very bad because you don't get signals anymore where you want to have signals. And on the other hand, you have a slow increase here if the width of the time interval goes up. And that's simply because you get a blurred image which has signal where the optimals where you don't want to have signals. That's why the measure goes bad here. And so of course what you then get is somewhere there's an optimum. It's around a delta of 0.5 meters over c. And then that is for 10 million photons. The distance from here to here is the fundamental limit in the simple model. Basically, this is expected to happen all the time. You have a trade-off. You need to cut to deblur your image. If you cut too much, you lose the signal. So that's expected, and this is a way how you can quantify that. So these images are certainly not doing justice what you can do with it, because this is not a very nice reconstruction of the square in the background. But don't forget, we have 3D information now. And so what we could do now is we get some directional information from the incoming photons, the direction, a unit vector where the photon comes from. And you also have the time of flight. And if the detector and laser are close by, and there's not much scattering involved, it's mainly forward direction, then roughly t/2 is giving you the distance where the object is. So what you could do is take the directional information from your photons, take half of the time of flight, and then you reconstruct the scatter center in 3D space. That assumes, of course, sort of a linear propagation, and we already know that's not true because we got a lot of scattering in between. But I have told you what you can do with the cuts in the time of flight. You can concentrate on the photons which do not scatter. You eliminate with a cut in time of flight. You put your starting measurement time at the onset time, and then you make your width as small as possible you can afford, and that cuts out the photons which scatter, and you just predominantly get photon without scattering. So that shouldn't be then a bad approximation. And that does work quite nicely. So this is, again, the 3D reconstructions without any cuts. It's not very good. First of all, our plate at 50 meters is blurred as we would have expected. And here you see an onset of the screen, but it has a hole in the middle. So that is also not what's happening. So let's use the cuts which we have in the laser situation. So if we do that, this is a time of flight histogram you have already seen. So here at 20 are the early photons coming directly from the screen. So this is a signal from the screen. Here 30 meters over c is the time and the photons come back from something behind the screen. And the red bar now indicates the cuts which I have applied. So there's a cut between 20 and 24. And then I don't consider photons coming in here. And then we already know that for deblurring, the optimum is around between 30 and 30.5. That gives us the optimum deblurring from the 2D images. So we apply a cut here and the second peak. And if you do that, you get this image. And now you see nicely the screen at 10 meters. So here is 9 meter, 10 meters. So the laser is down here somewhere. This is the screen. And down here at 50 meter distance, you get a reconstruction, a 3D reconstruction of the object of interest, which is our metallic plate. You also see this is the screen in principle mathematically was infinite, but because you have to shine to illuminate the scene with the laser, this is basically the cone of the laser light which you see, and that's a reconstruction of the scene. So what you basically are now doing is you indeed are looking behind the screen and you can see the object. Of course, there is something, there's this fundamental limitation, some blur you can't remove if you have a limited number of photons. In this case, in the simulation, it was around 10 millions. Okay, so that's just from the simple model and from the simulation subgroup in our discussion group. And then we discussed how can you improve things. First of all, I think what's really interesting is maybe you can use a polarized light. There's a lot of shortcomings in the modeling because we haven't taken into account the Poisson noise in the measurements of the time of flight. But what you would get is if polarized lights, laser light scatters of metal, you would know the change of polarization. If then the photon comes back and has elastic scattering from leaves, it all would change the axis of polarization. So polarization is another way you can apply a cut to your data, and this cut might not be affected by the Poisson noise in the flight of direction. There's a lot of other things coming in here, which we discussed. We could use 2 laser frequencies, and you could entangled photons was a suggestion from the group, from the wider group. This is indeed an area on its own. It's called quantum radar. It's an interesting development. At the moment, the problem is coherence over quantum coherence over long distance. And so far you can go up to 1 meter, but this is not what we want to achieve here. But the promises are great because this is, with entanglement, this is a method you can't jam. So this is a direction which we could explore further. So now this ray tracing is a very intuitive and maybe oversimplified model, but it can be viewed as a solution of radiative transport equation, which is behind and can model much more subtle effects. And the radiative transport equation is used, for instance, in LiDAR, and we have some experts talking about that. And at this stage, I hand over to, I guess, Oliver, who will talk more about the development in this direction.
Okay, yeah, thank you very much, Kurt. So I try to share my screen now. Let me see. I hope everybody can see the same as in the previous screen, just it goes on here from my screen. So the next step in our consideration was how can we generalize what we did and incorporate maybe more features and more details of the physical scenery. Kurt mentioned already the radiative transfer equation. You can see it on the screen, hopefully. It is an integral differential equation. It is used actually in many applications. I will explain a few of them a little bit later on. Let me first explain the general structure of the equation. If you look at the equation, the first 2 terms on the left provide a transport term. And the third term on the left is something like a dissipation or attenuation term. And on the right, you have some gain. So it's essentially a balance equation. And you consider light or whatever you want to model as particles, a density of particles. They can propagate along straight lines in this model here. Theta is the direction of this straight line. C is the velocity of the particles. T is time. U is the density. And A of x gives something like a loss term, which all the loss terms can be collected on the left. If you are looking at an infinitesimal volume, on the right you have the gains. And if there's no scattering at all, you can forget about the integral term. Then you just go along straight lines. Q of x is our source term, which in our case would be the laser. If there is scattering, this integral term pops up, and the B of x is then also incorporated in the A of x on the left. So some of the disappearing part on the left, in the I of x, gets back into different directions on the right by the integral term, which is the scattering term. In the scattering term, you see the eta. This is the scattering cross-section. This tells you something about how the scattering takes place. And you can use different models. What I have shown here in this transparency is something like a very general standard model. You have conservation in a pure scattering event, conservation of particles, which is this next equation. And which scattering behavior you use is also depends on the physics. A popular model is a Hennier-Greenstein model, which you see on the third equation on the slide. You can use other models in order to model specific physics. You can actually also in the equation, on the radiative transfer equation, add more terms, more scattering terms if you have, for example, different scattering events mixed with each other. I mentioned also on the slide initial and boundary conditions. Certainly this is the integral PDE. You might want to put an initial condition and a boundary condition. Now, if you start thinking about the inverse problem, you are also thinking of a target which you want to resolve. The scattering takes place if you now get rid of the idea of a single screen and now think in terms of a forest. A forest will scatter everywhere on the path from the source to the target and back. So you have volume scattering. So basically this eta, this integral, is space dependent. At every position x, you have a scattering event. Theta is the direction which you consider, and t is time. But the targets, how do you put the target into this? This could be a boundary condition if you think of this as an inverse problem, because maybe the target is something which is not a forest, right? But this is, if you later want to tackle the inverse problem, you have to make a decision on that. You could also try to add an additional term into this integral differential equation which you want to recover. So this is just, in the nutshell, what is the model? Light is considered as a particle, and they can scatter to a certain degree. Now this model has many applications. I've listed here a few applications in this application section. You can read this. In biomedical imaging, you might have heard about optical tomography, fluorescence tomography, very popular in recent years. Probably originally it comes from atmospheric physics. If you want to understand stellar atmospheres with a telescope, some blurring goes on when the light comes from the stars to the telescope. You want to get rid of this blurring. Computer graphics, of course, if you want to model sceneries with fog or something, you have a very similar model. Even also in seismic imaging, you have a kind of seismic waves which you can model with such a particle idea. Nuclear reactor physics, one of the major applications in maybe 50 years ago, where you want to model neutrons, or underwater communication and more. So this is a general model. How can you do this in a computer? In a computer, you can use Monte Carlo simulation where you just model each individual particle with a random number generator and let it go through a random walk basically. And you just do this in parallel if you want 1 million of times and you sum up what you get. Or you can try to discretize directly this transport equation here by finite differences, finite elements, spectral methods. Or you could actually make use of the structure we're having the integral there and expand into a Neumann series or Born series and so on. So this can be done. It depends on your physics. Now in our applications, the important question to ask is, what type of element should we put in this transport equation, and what effect would it have on our signals when we want to solve the inverse problem? And I want to show you you remember there were these parameters B and A, I go back here, A on the left and B on the right. And there's also this eta, which contains this single parameter G. G in the Hennier-Greenstein model tells you something about whether scattering is 0, or it is backscattering, then it becomes negative, or it is highly forward scattering, it becomes positive close to 1. This is the Hennier-Greenstein model. So if you want to understand what is going on, so we did some Monte Carlo simulation here, and in 2D actually, for different combination of these parameters. And if you just have very few scattering events, so the B is very small, saying it's almost no forest there, then you see this propagation of a single pulse through the domain. Or the 10 figures you see there are time snapshots of the propagation of the photon. You see a small wake which comes through this a little bit of scattering. Now, if you increase the B, so the scattering events, so the number of scattering events, probability of being scattered, the number of trees, if you wish, or the foliage, you see this wake here, so it becomes stronger, scattered light becomes stronger. If you use certain combination of B and G, which is highly forward peaked, actually it becomes almost like a wave phenomenon, which you can observe, which is kind of, you can approximate it by a telegraph equation. Now you see there's a blurring going on in the signal already. You will see these blurrings in the data as well. You have to take care of this. Now, if you have a highly scattering environment, you see it here, the B becomes very large. So if there are lots of trees or lots of scattering going on, then you don't really see signal propagation anymore. You lose the directional information, and you might even lose the time information to a certain degree. So, so time of flight information. So this is almost diffusive. And in fact, often the diffusion model is used for modeling this. And if you look at data, this is just a general description of data. If you look at the boundaries of the box, which I have described here, you see here, it's a source location. You get backscattered light almost immediately, because if you are in a forest and you are backscattering, the early photons might actually come from the forest itself and not from the target. So you might need some additional techniques or means using inverse problems or whatever you have, polarization or filtering to distinguish and differentiate these different signals from each other. So this is basically what I wanted to say. So if you want to do the inverse problem in multiple dimensions means you have 3 space dimensions, 2 angular dimensions, and 1 time dimension. This is actually 3 angular dimensions. So it depends on whether the forest is 3-dimensional or 2-dimensional for you. So you can figure out it's a highly dimensional optimization problem. If you want to do this, you have to first figure out what are my parameters in my model and what type of propagation am I looking at. So the next speaker, Sean, will give you an idea of how this can be handled by looking at a 1-dimensional model, which I will hand it over to Sean right now, where you just cut down the spatial dimensions, and this will come also with a reduction of the angular dimensions. So maybe Sean, if you can carry over here from here.
Sorry, I'll just interject. Guys, how much longer you think you're going to need? I'm very conscious of the time.
I'll try to be quite quick.
Okay, thank you.
Sorry, okay, I'm going to share my screen. Right, so this is where we were in the presentation. As Oliver was saying, if you use a general RTE model, it's very high dimensional and difficult to get anything out. It's a very difficult inverse problem. And so this motivates trying to reduce the dimensionality to consider a 1-dimensional model. And in the case we're considering, the 1 dimension makes sense because we have a laser pointing and the photons move out. They're very collimated along the laser, and then they bounce off some target and then they come back. And so we might want to consider just the 1 dimension, which is the range along the path of the laser. And so if we write the radio transport equation in 1 dimension, we have these 2 equations that are shown here. That the right-hand side is the scattering, and when we have an integral in these 1 dimension, we would just have the single term. So there's some scattering, and so the UR represents the intensity moving out along the beam to the right. I'm thinking of it UL moving back along the beam. And this type of model would not capture any scattering out of the single beam, which is probably not very realistic. But I've just looked at this as an initial case. I wonder, one idea to extend this would be to try to incorporate into this 1D model the scattering which occurs out of the beam, as was shown in the earlier pictures from Kurt. But yeah, Oliver mentioned there's initial conditions. So there would be an initial condition at the source of the laser that models the shape of the pulse. And then you could then expand the photons moving to the right and left, UR and UL, in the scattering series. So these terms in the series each represent photons that are scattered a certain number of times. I'll just, I mean, I know that these formulas are probably complicated and too much to take in, but you can consider each of the terms in the series and iteratively solve for them. So once you know the 0 terms, you can then solve for the 1st order terms and so on and so on. And the 0 order terms with the conditions I've given here are simply the initial signal moving to the right and attenuated according to the attenuation of the medium. And so these would be the equations you would solve in order to calculate all the terms in the scattering series. And I maybe would add that you could incorporate the delta function for H in order to get an idea of what the impulse response is, and try to determine how much delta function and pulse would spread out under a model like this, which is the important thing to know, how much the delta impulse response spreads out in order to determine the fundamental limit of the system. So that was what I was going to say about one-dimensional models. There was also another section which was contributed by Nick. Is Nick here? Otherwise, I'll maybe say a few words about it, but this is actually a work by Nick. And it's an example of using the RTE in a certain inverse problem. And there's an additional factor here, which is that there's actually two frequencies which have different attenuations. And so we have this radiative transport equation here, same as Oliver, slightly different notation, but the same equation that Oliver presented earlier. And there's two different frequencies of light, and they have different attenuations, which is the key idea in what Nick was presenting, and possibly an idea that could be used in this single photon setup. And the different attenuations allow you to make an image based on the contrast and the attenuation. And so this is details of the model, and the image actually is the difference, the contrast between the two attenuations. And so these are just demonstrations, I believe, that Nick has done. And so what he's actually trying to find is this is a three-dimensional case, and they're trying to find a smoke plume, which scatters in a certain amount by shining a laser on it and then detecting what returns. And then, so these are the ground truth models from two different views of the smoke plume. And then looking actually at the attenuation contrast between the two different frequencies, it is able to model or image the smoke plume with these errors from the same two different views. Okay, I guess I think that's everything we have. I'll stop there in the interest of time.
All right, thank you all very much, Kurt, Oliver and Sean. I very much appreciated. Clearly a lot of work gone in there. I wonder if we can have an end user perspective. I think Milo from DSTL was involved in this challenge, or if there's somebody else, if not Milo.
Milo had to unfortunately leave. He wasn't able to, but he passed on his thoughts to me. Yeah, he was really, really impressed and really grateful for all the work. And yeah, there was a bit of physics to get our heads around at the beginning, but the work has progressed hugely, and it's such a small team. But yeah, he's very excited to potentially take all of these directions further forward. Yeah, I don't know if Richard, you wanted to add anything.
No, probably not. Just thank you very much to all the academics for their input, which has been gone a very long way in a very short amount of time.
Yeah.
Okay, well, thank you. Maybe we can just squeeze in one very quick question if anyone has one. Otherwise, as I say, those breakout groups will be available, and people can ask to get moved into them after we've done our short wrap up for any further questions. Does anyone have something they'd like to ask now? Okay, well, so I think David Abrahams, the director of the Isaac Newton Institute, was just going to say a quick word, probably another thank you. And I think to sort of wrap up, I think Rob from DSTL was going to say a few words as well. Oh, and just to say, there's been a lot of very interesting information put into the chat. We will save that and we will share it with you all probably at some point next week when we send our thank you email. So just to let you know, we will capture all that.
Great, thanks Jane. So as Jane said, I'm David Abrahams. I'm the current director of the Isaac Newton Institute, and I'd like to start by thanking the Gateway team for organising this event. We had hoped that we would get a few people in our building by now, but alas, that wasn't the case. And so it was a slight worry that compared with the very successful meeting in January, which was a physical meeting, a traditional one, study group type, that this could be a little bit more challenging. But as it happens, everyone gets into using the Zoom way of working with breakout groups, and I greatly appreciate the extra effort you've had to go to allow it to work, and everyone seems to have done it very well, so thank you very much. Yeah, as Jane says, I need to thank a few people. So I said the Gateway team have been amazing. Thanks, Lizzie, and thanks, Jane, for being our Master of Ceremony. But I'd like to go back to our original discussions that Jane and I had quite a while ago, probably 2018, with Kevin Wagstaff and Francis Watson from DSTL, about getting the maths community engaging more on the electromagnetic problems. We know that there's a few people, especially the inverse people in our community, who engage on these problems, but we don't have a great critical mass in this country of EM specialists from the mathematics community. So very much from the outset, we were thinking about trying to create that community. And it's wonderful to see that we've got around 70 people in the audience today, to show that that's a carryover from January. So it is a success. And I believe that what happens next, taking these problems forward, will cement that, that community. And that's what the Gateway and the Newton Institute is trying to generate. But of course, it couldn't have been achieved so successfully without our partnering with PA Consulting. I think it has worked very well. So I'd like to thank Rob Lambert and James Matthews in particular, and all of the PA Consulting team for doing a grand job of working with us so closely and coming up with great problems and allowing those to be turned into really good study group type problems. I'd like to thank Emily Russell and Emma Bowley from DSTL for working closely with us, and all the DSTL team. And last but not least, I should remember our expert panel of Alan Champneys, Eddie Wilson, Bill Lionheart and Tony Mulholland, who've really helped us scope this. And without their input, it wouldn't have been the success it has been. I think it's been remarkably interesting and exciting this week. And last but not least, I want to thank all the participants. Thank you for coming along. And we're really grateful for this journey we're going on. And I believe we're set to continue. There's some great potential work following on. And I'm sure whoever's going to speak next will talk about wanting to just use this as a starting point. We have money and resource to try and make sure that these are turned into really interesting long-term projects. And we will, from the Newton Institute, do everything we can to support that as well. So with that I'll pass back. Thank you, Jane.
Thank you. I think Rob Lambert was going to say a few words.
Before I do, can I invite Lieutenant Colonel Adrian Moth to add a few thoughts from the user world.
Yeah, absolutely. Good afternoon to you. Lieutenant Colonel Adrian Moth. I'm lead for providing EW capability development, excuse me, into Army headquarters, so across the Army. And coming to these kind of conferences is absolutely fascinating for us to see where people are thinking, what people are thinking about, and the problems they are trying to solve. So I was asked to sort of think about the value of these conferences, and absolutely incredible value and important to us as a practitioner that this kind of work continues, and I hope it does continue. And I'd certainly like to be involved in the future conferences that you have. And I think it's just as a general point, it's absolutely imperative for us as the Army. I mean, we're often accused of fighting the last war. It'd be useful that we keep ahead of the, shall we say, the competitor, and make sure that we have a stream of thinkers and problem solvers and designers, inventors, or whatever you want to call them, that can supply us with the sort of tools to maintain that military advantage. I think just by way of an example, we may or may not, hopefully we will, get a program where we can develop the next generation of EW capability. And the likelihood is there'll be a rolling program. And to have a successful rolling program, we need that sort of carpet undercurrent of innovation, continual strand of innovation, giving us those ideas, fueling our thought processes, and telling us where the sort of emergent technology is that we need to be getting after. So I'm absolutely keen to be involved, closely involved in this program any way I can. Back to you.
Thanks, Adrian. I just want to say a few last thank yous. Well, very quick, and I think David very eloquently covered the thanks to the wide range of people who've been contributed to making what's, certainly from my perspective, was a hugely successful week. Obviously, a number of you were there, joined us back in January, and we had a more traditional physical meeting. The world has changed fundamentally since then, and we're here sitting using virtual tools. And so my sense is that it's been a completely different way of engaging, and yet the outputs that everyone's achieved have been phenomenal. They're really great. And I'm really looking forward to the chance of being able to read through some of the papers, or the papers that have been generated by the various challenges. So thank you again from everyone. It's been all about, as David says, all about building that community of interest from the mathematical community, joining in and engaging this world that Adrian was describing just now. Great to see it happening, great to see some outputs. Going forwards, there is funding in place to take, to accelerate some of these challenges directly within the programme. And equally, you will have noticed there have been a wide range of colleagues from DSGL have been on the call, and hopefully you'll have piqued some of their interests, and you might even get some contacts from them who might want to engage and pick up on some of that thinking. We're there as a programme to generate links between the DSGL team and the mathematical world, and the more of that happens, the better. Going into the, I guess, going beyond the immediate of taking some of those challenges forward. We have a study group planned for January. We're conscious it would be great to engage maybe a more junior group of academic mathematicians into this. So we're looking towards planning for that. And certainly the intent, as David said, is that this program will continue. We'll run another workshop similar to this next year. But overall, thanks everyone. We know what a busy time it is anyway. We know how particularly busy it is for all of you at this point in time. So thanks everybody. Thanks for a brilliant week. And finally, and just, I'm sure Lissy would say this, please could you fill in the feedback forms? We really do value the feedback we get. It helps us shape and grow and develop this event. Thanks everybody.
Thank you, Rob. Yes, yeah, I'll further underline the importance of feedback forms. So really, it's just a case of, for those who want to stay and have some further conversations, the breakout rooms are open. So if you can let Lissy know which room you'd like to be allocated into. Lissy, I don't know if you've got a particular protocol you want to follow for this.
No, I guess probably in the chat might be the easiest, I suppose.
And one last request that I should have made: could all of each of the challenges share their reports as they stand today and the presentations with Lissy? Appreciate some of you may choose to want to mature them further. It'd be great to have a baseline of where we got to the end of this week.
And if you can share some of the raw content as well, because we may end up incorporating all this into one report. So if it's LaTeX, overleaf, collaboration links, whatever works, pass them to Lizzie, and she'll pass along to us to bring those through. Thank you.